If you walked outside right now, looked up at the 200 billion stars in our galaxy alone, and asked, "Where is everybody?" what do you think the universe would say? You probably imagine that the distances are simply too vast, or that we have not been listening long enough. But the math says the opposite. In 13.8 billion years, somebody should already be answering. They are not. And that absence has a specific name. Tonight, we count the years that have passed, the stars that have burned, and the civilizations that should already be echoing back across the void, and hear what their silence is actually telling us about the road ahead. Before we dive in, if you love exploring deep questions of the cosmos as much as we do, take a second to like the video or subscribe, and tell me where you're listening from and what time it is. Now, let's begin. There is a question so simple that a child can ask it, and so weighted that professional scientists have devoted entire careers to not answering it. The question is this: where is everybody? Not just where are the radio signals, not just where are the probes, or the megastructures, or the faint chemical traces of industry drifting across the light of distant stars. Where is anyone at all? Where is any evidence in any form, across any wavelength, of minds other than our own having ever looked up from their own world and wondered the same thing we are wondering right now? The universe is approximately 13.8 billion years old. It contains somewhere in the range of 2 trillion galaxies, each hosting hundreds of billions of stars on average. The Milky Way alone, the one we live inside, the one we call home, contains roughly 200 billion stars, and current estimates from the Kepler Space Telescope's survey work, completed in the early 2000s, suggest that most of those stars host planets, and that a conservative fraction of those planets sit within what astronomers call the habitable zone, the orbital belt where liquid water can persist on a rocky surface. The numbers, stacked like this, seem to guarantee company. They seem to demand it. They seem to make solitude not just unlikely, but statistically absurd. And yet, the sky is quiet. The instruments are quiet. The most sensitive radio listening apparatus our civilization has ever assembled, pointed for more than 60 years at thousands of stars across the galactic disk, has returned nothing that holds up. Not a structured narrowband signal, not a repeating pattern, not one solitary transmission that could not be explained as interference from our own civilization bouncing back at us in some unexpected way. The Breakthrough Listen program, now headquartered at the University of Oxford after its 2023 move from UC Berkeley, and described as the most comprehensive search for technosignatures ever undertaken, has spent years pointing the world's largest radio telescopes at millions of targets. As of a 2024 paper analyzing the Green Bank Telescope archive, an analysis of 9,684 observation cadences covering 3,077 stars, the finding was unambiguous. No credible technosignature candidates remained after scrutiny. This collision between what the numbers predict and what the observations return is the Fermi paradox. It is named, somewhat loosely, for Enrico Fermi, the Italian-American physicist and Nobel laureate, who, in 1950, was having lunch at Los Alamos National Laboratory in New Mexico with his colleagues Edward Teller, Herbert York, and Emil Konopinski. The conversation had drifted, as conversations at Los Alamos sometimes did, towards something strange. Fermi reportedly looked up from his food, perhaps mid-sentence on some other topic, and simply asked, "Where are they?" His colleagues knew immediately what he meant, and nobody could answer. The lightness of the moment, a casual lunch, a brilliant man, a question that could not be deflected, has made it one of the most famous exchanges in the history of scientific thought. But here is what often gets lost in the retelling. Fermi was not the first to feel the weight of that question. In 1975, the astrophysicist Michael Hart published a formal paper in the Quarterly Journal of the Royal Astronomical Society, arguing that if any civilization capable of interstellar travel existed anywhere in the galaxy, it would, given enough time, colonize the entire Milky Way. The galaxy is old enough, and travel, even at a modest fraction of the speed of light, is fast enough over geological timescales that a single spacefaring species starting anywhere would eventually spread everywhere. Hart called the absence of these visitors a fact demanding explanation, not a puzzle to be filed away, but a hard constraint on what the universe could contain. His argument became known as the Hart-Tipler conjecture, after mathematical physicist and cosmologist Frank Tipler extended it in 1980, and it sits at the foundation of every serious discussion of the Fermi paradox that followed. Now pause here for a moment, because this is where the weight of the argument begins to accumulate. What the Fermi paradox is really asking is not simply where the aliens are. It is asking us to reconcile two things that cannot both be true at the same time. Either the conditions for intelligent life are so rare that we happen to be the only example in a galaxy of 200 billion stars across a history of 13 billion years, which strains every intuition we have about what a large sample should produce. Or the conditions for intelligent life are not rare at all, meaning that many civilizations should have arisen, and some barrier, some universal mechanism, is preventing us from seeing any of them. Either answer, held fully in the mind, produces a very specific kind of vertigo. Either we are cosmically alone, which is one kind of staggering, or we are cosmically surrounded by something that, for reasons we cannot determine, is not making itself known, which is an entirely different and arguably heavier kind of staggering. The standard framing of the paradox rests on a calculation introduced in 1961 by the astronomer and SETI pioneer Frank Drake, who was then working at the National Radio Astronomy Observatory in Green Bank, West Virginia. Drake convened what is now considered the first SETI conference, a gathering of scientists who met to seriously and systematically ask, for the first time, how many communicating civilizations might exist in the galaxy at any given moment. To organize the conversation, Drake wrote an equation on a chalkboard. It became one of the most famous pieces of mathematical notation in the history of science, not because it gives a definitive answer, but because it maps the shape of our ignorance with extraordinary precision. The Drake equation multiplies together a sequence of terms. You start with the rate at which stars form in the galaxy each year, roughly a few to 7 new stars per year, a number that is reasonably well constrained by observation. You then multiply by the fraction of those stars that have planets. You then multiply by the average number of planets per star that could support life. You multiply by the fraction of those that actually develop life. Then the fraction where life becomes intelligent. Then the fraction where intelligent life develops detectable technology. And finally, by L, the average length of time such a civilization remains detectable. That last term is the one that swallows everything. Nobody knows what L is. It could be millions of years if civilizations are stable. It could be decades if civilizations routinely destroy themselves or go silent for reasons we cannot predict. The profound honesty of the Drake equation is that it converts a question we cannot answer into a question we can at least argue about rigorously. Some estimates for the number of communicating civilizations currently active in the Milky Way run as low as 1, us, and as high as millions. A 2016 revision by astrophysicists Adam Frank at the University of Rochester and Woodruff Sullivan at the University of Washington took a different approach. Instead of estimating how many civilizations exist now, they estimated the total number of technological civilizations that have ever arisen across cosmic history. Their conclusion was that humanity is unlikely to be the only technological civilization the universe has ever produced, unless the probability of a civilization arising on any given habitable planet is smaller than roughly 1 in 10 billion trillion, a probability threshold they called the pessimism line, so small that even modestly optimistic assumptions imply many civilizations have come before us across cosmic history. That number is not a comfort. It makes the silence harder to explain, not easier. This is where the paradox sharpens into something that moves beyond astronomy and begins to feel personal. If civilizations arise, they presumably develop technology. Technology implies energy use, and energy use leaves signatures. A civilization that has been expanding and using energy for even a few thousand years should be visible in some form. In the waste heat of its industry, in the radio signals it leaks into space as a byproduct of its communications, in the chemical fingerprints of its industry drifting across the light of its host star, or in structures large enough to alter the behavior of that star itself. The physicist Freeman Dyson proposed in 1960 that a sufficiently advanced civilization would eventually build a sphere of collectors around its home star to capture all available energy. A structure so large, it would make the star appear dim in visible light and bright in infrared. We have looked for such structures. We have not found them. Some researchers suggest we would find them if we looked harder. Others point out that we have looked very hard indeed, and the infrared sky is not full of them. The numbers, taken seriously, produce a specific and haunting conclusion. In a galaxy 13 billion years old, with hundreds of billions of stars, and with planets forming around most of them, a civilization that arose even 5 million years before us, a blink in cosmic terms, could have had time to colonize every habitable system in the Milky Way. We should not merely be receiving signals from the civilization next door. We should be surrounded by the physical footprint of expansion that has had geological timescales to unfold. The galaxy should look, in some detectable way, occupied. It does not. And so we are left with the question that is the subject of everything that follows. Not just where are the signals, but where is the evidence? Where are the ruins? Where are the artifacts? Where is any trace at all of the minds that came before us, in a universe that has had 13 billion years in which to produce them? That question has exactly 2 categories of answer, and both categories are, on careful inspection, profoundly heavy in ways that are not immediately obvious. The first category says, they are not out there because they never arose, or never survived, or never expanded in a way we could see. Life, or intelligence, or durable civilization is rarer than our intuitions suggest. So rare, perhaps, that we are the first, or one of the first, or isolated enough from any others that the distances are simply too vast. This category places a filter somewhere in our past or our present. It says that something in the long chain from dead chemistry to radio telescope is extraordinarily improbable, perhaps many things, and that we somehow passed through whatever tests the universe applies and came out the other side capable of asking the question. The second category says, they are out there, but we cannot see them because they are hiding, or they have collapsed before they could announce themselves, or they are operating in ways we do not recognize, or they have transcended the kind of existence that leaves detectable traces. This category places the filter somewhere in our future, or proposes an explanation for the silence that does not require rarity. And some of these explanations are, on careful examination, not reassuring at all. Both categories, taken seriously, demand something from us. They demand that we revise our picture of what the universe is, what life means within it, and what kind of future is actually available to a civilization like ours. That demand is what the Fermi paradox actually is. It is not a puzzle about radio signals. It is a mirror, and what it reflects back is the question of whether we are a beginning or an ending. Take stock of where we are before going further. We have established the basic observational fact. 60+ years of systematic listening have returned nothing credible. We have established the mathematical framework through which that silence is rendered paradoxical. A universe this old, this large, this full of stars and planets should not be this quiet. And we have established the two great categories of response. Either the universe is emptier than it looks, because something in the path from matter to mind is almost impossibly hard, or the universe is more complicated than it looks, because minds exist but are not visible to us for reasons that range from the mundane to the deeply unsettling. Each of these branches deserves time. Each deserves to be walked slowly, with attention given not just to the mechanics, but to the weight of what the mechanics imply. Because the Fermi paradox is not merely a question for astronomers. It is a question for everyone who has ever wondered, on a clear night, looking up at a sky genuinely thick with ancient light, what it means to be here. The story begins, as so many things begin, with the structure of what exists. And to understand what that structure should have produced, we need to understand what it actually produced in the one case we know about, Earth, and the 3 billion year chain of contingency that ended with a species capable of asking whether it is alone. The Sun is approximately 4.6 billion years old. Earth condensed from the same disk of gas and dust at roughly the same time. The earliest widely accepted evidence of life on Earth, putative stromatolite structures in ancient rock formations in the Isua greenstone belt of Greenland, has been dated to approximately 3.7 billion years ago, with somewhat younger but more robust microbial fossils from the Pilbara region of Western Australia at around 3.48 billion years ago. Meaning that life appeared on this planet within perhaps a few 100 million years of the planet becoming hospitable. That is a cosmically short delay. If life arose on Earth quickly by geological standards, that might seem to argue that life appears wherever conditions allow, that it is not especially rare. And for some time, this was taken as encouraging news. But here is where the textbook version of the story begins to show its seams. Single-celled life appeared quickly. Then, for almost 2 billion years, nothing much happened. The biosphere consisted of bacteria and archaea. It was alive. It was metabolically active. It was doing what life does. But it was profoundly simple by any measure that matters to the question of detectable intelligence. The transition from single-celled life to complex cells with nuclei, what biologists call eukaryotes, appears to have happened roughly 1.8 to 2 billion years ago. And it happened, as far as we can tell, exactly once. Not twice, not independently in multiple lineages, but once in a single endosymbiotic event in which one ancient bacterium was engulfed by another and never digested, eventually becoming the mitochondrion, the energy-generating structure inside every complex cell alive today. From a single event, in 2 billion years of opportunity. And from eukaryotes, the road to multicellular life, to creatures with organs, nervous systems, brains, took another billion years, and also appears to have been vanishingly rare in its transitions. The evolution of the nucleus, of sexual reproduction, of true multicellularity, of animal body plans. Each of these looks, in retrospect, not like an inevitable step on a smooth ramp, but like an accident, a confluence of conditions so specific that it could easily not have happened at all. This is the foundation on which everything else rests. Not the simple existence of life, but the fragility of the path from simple life to complex life to intelligent life. A path that took 3.5 billion years on this planet, with no guarantee at any stage that the next step would be taken. A path on which, if you rewound the tape of Earth's history and played it again, as the paleontologist Stephen Jay Gould famously argued, there is no reason to believe the same outcome would recur. That is the ground beneath our feet. And the sky above it is silent. Everything that follows from here is an attempt to explain why. The universe made stars before it made life. This seems obvious, but the sequence matters more than it first appears, because the earliest stars in cosmic history, the ones that blazed into existence in the first few 100 million years after the Big Bang, were almost entirely useless for producing anything biologically interesting. They were made almost entirely of hydrogen and helium, the two elements that emerged from the first few minutes of the universe's existence, and they burned fast and died violently, seeding space with the heavier elements that did not exist before. Carbon, oxygen, nitrogen, iron, phosphorus, the elements that life as we know it requires, had to be forged inside stellar cores and scattered by supernova explosions before any planet capable of hosting chemistry worth calling alive could condense from the debris. This is the first constraint on the distribution of life in the universe. The universe had to age enough to produce the right ingredients. And by current estimates, the stellar generation capable of hosting rocky, chemically complex planets in stable orbits, what astronomers sometimes call population 1 stars, meaning stars enriched with heavy elements, did not become common until several billion years into cosmic history. Our Sun, at 4.6 billion years old, is a relatively young star in the context of the galaxy's 13 billion year history. But it is also old enough to have formed from material that had already been through multiple stellar generations of processing. The heavy elements in your bones, in the carbon of every cell in your body, were made inside stars that died before the Sun was born. The galaxy, in other words, needed time to become fertile. And once it becomes fertile, the question of how long it takes to go from chemistry to civilization becomes the central uncertainty around which every version of the Fermi paradox turns. Here is the problem, stated plainly. If the process of going from chemistry to intelligence takes on average roughly 4 billion years, which is roughly what it took on Earth, then civilizations that began their journey in the early universe should be finishing it now, or should have finished it some time ago. Stars old enough and chemically rich enough to host complex planets have existed for at least 8 to 10 billion years in parts of our galaxy. That is twice the time it took life to evolve on Earth. In principle, civilizations could be anywhere from a few hundred years more advanced than us to billions of years more advanced. The range is incomprehensible. A civilization that is 1 billion years older than humanity would have had time to explore every corner of the Milky Way, construct structures on scales that would be visible to our telescopes, and do things for which we do not even have concepts. And yet, nothing. Pause here, because something specific needs to be held for a moment. The question is not whether intelligent life could arise elsewhere. Almost nobody who thinks carefully about this denies the chemical plausibility of life. The question is whether the particular sequence of transitions, from chemistry to replication, from replication to cells, from cells to nuclei, from nuclei to multicellularity, from multicellularity to nervous systems, from nervous systems to language and technology, is something the universe does readily, or something it does almost never. And the honest answer, as of this moment in scientific history, is that we do not know. We have one data point, one planet, one chain. And from one chain, you cannot determine whether the chain is common or miraculous. This is the first explicit admission of uncertainty that must live at the heart of any honest account of the Fermi paradox. We cannot determine, from Earth's example alone, whether the emergence of intelligence is a near-universal outcome of chemistry given time, or a vanishingly rare accident that happened to us and almost nothing else. Some researchers think it is common. The astronomer Carl Sagan spent much of his career arguing that the conditions for life and eventually intelligence are written into the laws of chemistry so deeply that the universe is almost certainly teeming with minds. In his 1966 collaboration with Soviet astrophysicist Iosif Shklovsky, Intelligent Life in the Universe, and in later writings, Sagan argued that the sheer number of opportunities across billions of galaxies made solitude essentially impossible. Other researchers think it is extraordinarily rare. The paleontologist Peter Ward and astronomer Joe Kirschvink, writing in the tradition of the rare Earth hypothesis, have argued that the specific conditions on Earth, the size of our moon, the position of Jupiter as a gravitational shield, the presence of plate tectonics, the timing of the Great Oxidation Event, the particular character of our Sun, constitute a convergence so unlikely that Earth-like outcomes may be separated by distances so vast as to make contact essentially impossible, regardless of how long civilizations last. Both views are held seriously by serious people. Both are consistent with the data, and both lead to different versions of the same heavy conclusion. Now we turn to the structure of what might be, blocking the path from matter to mind. Because the Fermi paradox has given rise to one concept that, once understood, changes the way you hear the silence. That concept is Robin Hanson's Great Filter. Hanson, an economist and researcher at George Mason University, published an essay in 1996, updated in 1998, with the deceptively quiet title, The Great Filter. Are we almost past it? The question in that title is not rhetorical. It is the most consequential question Hanson could think to ask, and it remains so today. The argument runs like this. If intelligent, expansionist life arose readily in the universe, we would see evidence of it. We do not see evidence of it. Therefore, something is filtering out that outcome. Something is preventing the emergence or the survival or the expansion of civilizations at a rate that would make them visible. That something, whatever it is the Great Filter. It is a barrier, or a set of barriers, somewhere in the long sequence from dead chemistry to detectable civilization, through which almost nothing passes. The question that Hanson asked, the question encoded in his essay's title, is where that filter is located relative to us. And the answer to that question divides into two possibilities, with profoundly different implications. The first possibility: the filter is behind us. It has already been passed. The filter was one of the early steps, the emergence of life from chemistry, or the transition from simple cells to complex cells, or the development of multicellularity and nervous systems. And it was so improbable that almost no planet in the galaxy has cleared it. We cleared it. We made it through, somehow, by a combination of conditions so specific and a series of accidents so improbable that we stand here now as something extraordinarily rare. If this is true, then the silence is explained. The universe is almost entirely empty of complex life, not because complexity is destroyed, but because it almost never forms. And our future is not foreclosed. We might be the beginning of something remarkable. The second possibility, the filter is ahead of us. It has not yet been passed. The filter is a barrier that every civilization eventually encounters, and almost none survive. Something in the process of becoming an advanced spacefaring species that reliably destroys or silences civilizations before they can announce themselves at a scale we could detect. If this is true, then every civilization that has arisen in the history of the galaxy has, at some point on the curve of its technological development, encountered something it could not overcome. And we are approaching that point now. This is the division that gives the great filter its weight. It is not merely an abstract distinction. The location of the filter changes what our current moment means. It changes what we should be afraid of. It changes what the silence is telling us. And here is where the argument produces its most counterintuitive implication. One that Nick Bostrom, the philosopher at the University of Oxford's Future of Humanity Institute, articulated with deliberate care in a 2008 essay titled, "Where Are They? Why I Hope the Search for Extraterrestrial Intelligence Finds Nothing." Bostrom's argument is this: finding life elsewhere would be bad news. Think carefully about why. If we find evidence of microbial life on Mars, simple, ancient, fossilized, or active, it tells us that life emerged independently in our own solar system. 2 data points, not one. And if life arose independently twice within the same solar system, then life's emergence from chemistry is probably not the great filter. It is probably common. Which means the filter must lie elsewhere, in the transitions from simple life to complex life, or from complex life to intelligence, or from intelligence to durable civilization. And if those transitions are not the filter either, if our finding of microbial Mars life is accompanied by evidence that complex life also arises elsewhere, then the filter must lie ahead of us, in something that every civilization encounters and almost none survive. Every discovery of life beyond Earth in this framework is a step toward the conclusion that the filter is in front of us. Every empty Petri dish, every null result from Mars, every sterile ocean moon is a data point suggesting the filter might be behind us. The bad news, in this context, is finding what we most want to find. This inversion, where the exciting discovery becomes the troubling one, is one of the most disorienting ideas in contemporary science. It does not make finding life bad in any simple moral sense. It simply changes the interpretation of what that finding means for the long-term prospects of civilizations. For Hansen, for Bostrom, and for the growing number of researchers who have taken this argument seriously, the discovery of independently evolved life on Mars or Europa, or any of the dozens of other candidate worlds now being evaluated, would be, in a very specific and considered sense, one of the most sobering findings in the history of science. This is worth dwelling on, because the textbook answer to the Fermi paradox, the casual version, the one that circulates in popular accounts, is something like, maybe intelligent life is rare, or maybe the distances are just too vast, and isn't it lovely that we are here to wonder about it? That version is comfortable. It is not wrong exactly, but it is incomplete in a way that matters. It smooths over the sharpest edge of the problem, which is the edge that Hansen and Bostrom are pointing at. That the silence might not be a background condition of the universe, but a warning, and that the warning might be addressed specifically and personally to us. Now we can begin to examine the individual candidates for what that filter might be. the specific steps in the long chain from chemistry to civilization where the path might narrow almost to nothing. There are several, and each deserves careful attention because each illuminates a different aspect of why the universe might be quiet. The first candidate is abiogenesis itself, the origin of life from non-living chemistry. This is the step about which we know the least, and the uncertainty is genuine. We do not have a confirmed, experimentally reproduced account of how the first self-replicating molecule emerged from the chemical soup of an early planet. The Miller-Urey experiment, conducted in 1953 by Stanley Miller and Harold Urey at the University of Chicago, demonstrated that amino acids, the building blocks of proteins, form readily from simple chemicals under conditions thought to resemble early Earth. That result remains significant. But amino acids are a very long way from a replicating system, and the distance between a puddle of amino acids and the first thing that could meaningfully be called alive is a distance that chemistry has not yet been clearly shown to cross spontaneously. Some researchers argue that life's origin was inevitable given the right conditions, that chemistry reliably produces self-organizing systems of increasing complexity, and that the approximately 800 million years it took for life to appear on Earth after the planet cooled is actually quite fast on a cosmic scale. Others argue that the specific architecture of even the simplest known cell, with its genetic code, its membrane, its machinery for translating information into structure, is so precisely configured that its spontaneous assembly from raw chemistry borders on the miraculous, and that the speed of its appearance on Earth simply tells us that when conditions are right, the first viable configuration snaps together quickly and does not tell us how likely that configuration is to arise in the first place. We do not know which of these views is correct. That is the second admission of uncertainty that must sit alongside the first. The second candidate for the great filter, and arguably the most compelling one in terms of the evidence available to us, is the eukaryotic transition, the emergence of the complex cell. For the first 2 billion years of life on Earth, everything that existed was prokaryotic, simple cells without a membrane-bound nucleus, without the elaborate internal machinery that complex life requires. Then, somewhere around 1.8 billion years ago, in an event that appears to have happened exactly once across the entire history of life on this planet, one bacterium was engulfed by another, and instead of being destroyed, it became a permanent resident, eventually becoming the mitochondrion. Every animal, every plant, every fungus, every complex organism on Earth descended from that single symbiotic event. The evolutionary biologist Nick Lane, writing in the early 2000s and through a series of papers extending into the 2020s, has argued that this transition was not just improbable, but almost paradoxically unlikely. That the specific energetic requirements of complex cells and the specific mechanism by which mitochondria provide the energy to meet those requirements represent a bottleneck so narrow that its successful crossing on Earth may have been a matter of geological fortune that could easily not have occurred. If Lane is right, and the argument has substantial support, though not universal agreement among biologists, then the eukaryotic transition is a strong candidate for the great filter. It is a step that took 2 billion years on a planet where life was already established and running. A planet where every possible niche for simple life was occupied, where chemistry was abundant and conditions were favorable, and yet where the transition to complexity waited and waited and waited. 2 billion years. In cosmic terms, that is not waiting. That is almost failing. Picture yourself standing in a vast, still forest at night. The trees are all identical, stretching in every direction, each one a prokaryote. alive, metabolizing, reproducing, but fundamentally simple. And then, once, somewhere in that forest, two trees become something new. Not two locations, one. And from that one location, every complex living thing on the planet eventually descends. The forest does not transform. The forest stays what it was. But from that single point of transition, an entirely different kind of life begins to branch outward. That image, one event, 2 billion years, an entire planet's complexity resting on a single accident, is not a comfortable image when you hold it alongside the question of how many other planets might have had their own billion years of bacterial life and never crossed that particular threshold. The third candidate is the Cambrian explosion, or rather, the extended period of animal evolution that eventually produced nervous systems complex enough to generate something like awareness. The Cambrian explosion, which began approximately 541 million years ago, saw an extraordinary diversification of animal body plans in what is, geologically speaking, a very short period. The trilobites, the arthropods, the precursors of every major animal lineage on Earth today. They emerged and diversified and competed in what looks, from the fossil record, like a burst of biological creativity without precedent. But the emergence of the nervous system, of centralized information processing, of a brain, was not an event but a gradient, and the particular gradient that produced vertebrates, and eventually mammals, and eventually primates, and eventually a primate that could build a radio telescope, involved a series of contingencies that the fossil record preserves only partially. The paleontologist Simon Conway Morris at the University of Cambridge has argued in a series of papers and books from the 1990s through the 2010s that convergent evolution, the repeated independent emergence of similar solutions to biological problems, suggests that the universe of possible life forms is constrained, and that intelligence of some kind is likely to emerge on any planet where life establishes itself and runs long enough. Eyes have evolved independently more than 40 times on Earth. Flight has evolved independently multiple times. Echolocation, photosynthesis, warm-bloodedness. These are not one-off inventions, but convergent solutions. Conway Morris argues that intelligence is likely another such convergence, and that other planets with complex life would eventually produce minds capable of technology. But this argument is contested. Stephen Jay Gould, Conway Morris's most famous intellectual sparring partner on this question, argued the opposite, that evolution is so deeply contingent, so dependent on historical accident, on the specific sequence of extinctions and recoveries that shaped what was available at each moment, that rewinding the tape of life on Earth and replaying it would produce something entirely different, and that intelligence of the specific kind we represent may be a much rarer outcome than convergence arguments suggest. Some researchers think Conway Morris is right. Others think Gould was right. The data does not definitively settle the question because we have one planet and one outcome. And from one outcome, neither universality nor rarity can be established. What can be said with confidence is this. The path from the first cell to Enrico Fermi, asking his question over lunch in Los Alamos, took approximately 3.7 billion years. Involved at least several transitions that appear to have been extraordinarily improbable, and produced a species that has existed in anything like its current form for less than 300,000 years. If the filter is in the past, it is almost certainly located in one of these transitions. If even one of them is a near impossibility on any given planet, the galaxy could be effectively empty of intelligence, and the silence would be completely explained. That is the hopeful reading of the Great Filter. Hopeful in the specific, limited sense that it means we are not doomed by something ahead of us, that we passed through whatever gauntlet the universe runs and came out the other side. But the hopeful reading depends on the filter being behind us, and the evidence that it is not, the evidence that points towards something ahead of us in our future, is what gives the paradox its darkest resonance. Take stock again. The structure of the problem is now visible. We have observational silence. We have the mathematics that makes that silence strange. We have the concept of the great filter as the resolution. We have the two branches of that concept: the filter behind us, which is hopeful, and the filter ahead of us, which is not. And we have the specific biological transitions that are candidates for the filter in our past: the origin of life, the eukaryotic transition, the emergence of animal nervous systems. Now we turn to the candidates for the filter in our future, the mechanisms by which civilizations might routinely fail to make themselves visible, not because they never arose, but because they arose, advanced, and then encountered something they could not survive. Because this is where the Fermi paradox stops being a question about astronomy and starts being a question about what kind of thing we are. The most immediately intuitive candidate for a future filter is self-destruction. A civilization that develops technology rapidly enough to gain access to nuclear weapons, engineered pathogens, or other extinction-scale tools before it has developed the wisdom and institutional stability to manage those tools is a civilization that might not last long. The window between becoming dangerous enough to destroy yourself and becoming stable enough to reliably prevent it may be narrow. And if it is narrow enough, if most civilizations that reach our level of technological development fail to navigate that window, then the silence is explained not by the rarity of intelligence, but by its tendency to burn itself out. This candidate is not abstract. We ourselves have lived within that window since 1945, when the United States detonated the first nuclear device at the Trinity test site in New Mexico, and the world entered an era in which a handful of decisions, by a handful of people, in a handful of countries, could, in principle, render the planet uninhabitable. We have come close to crossing that threshold. The Cuban Missile Crisis of 1962, during which Soviet submarine officer Vasily Arkhipov refused to authorize a nuclear torpedo launch without surface confirmation despite believing his vessel was under attack, is frequently cited as a moment when accident and individual judgment stood between civilization and something unrecoverable. There have been others, and the number of such moments has not decreased as our technology has advanced. Here is where the first explicit test of the great filter's hopeful narrative runs into trouble. The textbook answer, the reassuring one, is that civilizations intelligent enough to build technology are also intelligent enough to manage it. That the same cognitive capacity that produces nuclear weapons also produces international treaties, arms control frameworks, early warning systems, and the institutional infrastructure of deterrence. That intelligence is self-correcting, that the feedback loops of consequence teach civilizations to stabilize, and that any civilization that makes it through the technological adolescence of nuclear weapons will, by definition, have demonstrated the capacity for long-term coordination. This sounds plausible. The answer seems, on first hearing, obvious. But here is what that answer doesn't account for. The number of nuclear weapons in the arsenals of Earth's nuclear states did not decline smoothly to zero after the Cold War. It declined significantly, but then largely stabilized. New delivery systems have continued to be developed. New states have acquired nuclear capability. The non-proliferation architecture, while real, has not proven airtight. North Korea's program continued to advance through the 2000s and into the 2020s, despite concerted international pressure. And the specific character of the risk has evolved. The threat is no longer primarily superpower exchange, but the combination of more actors, less stable institutions, and technologies that lower the threshold for catastrophic action. Moreover, nuclear weapons are only one item in the menu of extinction-scale risks that an advanced civilization generates. Synthetic biology, the capacity to design and produce novel pathogens from first principles, is advancing at a rate that many biosecurity researchers describe as deeply concerning. The same revolution in biological understanding that is producing the next generation of cancer treatments and genetic therapies is also, as a structural feature of the technology, producing knowledge and tools that could be turned toward the creation of agents for which no natural immunity and no pre-existing treatment exists. The barrier to entry for such work is declining. The number of people with the relevant knowledge is growing. And the detection problem, identifying a novel engineered pathogen before it spreads, is extraordinarily difficult. The reassurance that intelligence is self-correcting looks different when you examine the actual trajectory of technological risk, rather than the theoretical capacity for institutions to respond to it. And it still looks different when you consider a second dimension of the problem, that the window in which a civilization must make critical decisions may be far shorter than the time required to build the institutions capable of making those decisions wisely. Some researchers argue that this technological adolescence, this period in which capability outpaces wisdom, is a near universal feature of intelligent civilizations, and that it constitutes a genuine filter. Not an absolute barrier, but a bottleneck so narrow that the majority of civilizations that enter it do not emerge from the other side in a form that can expand into the galaxy and make itself visible. The number that survive might be small. It might be vanishingly small. And if it is, that smallness would account for the silence. Consider this carefully. If 1 in a million civilizations survives its technological adolescence and goes on to become a long-lived spacefaring species, then even with 1 million civilizations having arisen in the Milky Way across its history, only one would be present at any given time. And the distances between star systems are large enough that a single civilization, even an expanding one, might not have reached us yet. The silence becomes at least partially explicable. Not entirely. The age of the galaxy still poses problems for this account, but the window of required coincidence narrows. But here is the more sobering version of this argument, the one that does not resolve so cleanly. If the filter in our future is not technological self-destruction, if civilizations routinely survive their nuclear adolescence, survive their biotechnology moment, survive whatever initial tests their own capabilities impose, then something else must be doing the filtering. And the candidates for that, something else, become progressively more mysterious and, in their own ways, more troubling. Some researchers have proposed that the filter is not external to civilizations, but internal to the nature of intelligence itself. That intelligent life, given sufficient time, tends not outward but inward. That the simulated environment, the virtual world, the computed reality becomes more attractive and more consuming than physical exploration. And that civilizations that reach a sufficient level of technological sophistication tend to disappear not into space, but into computation. That the silence is not the silence of death, but the silence of absorption, of minds so occupied with interior experience that they simply stop broadcasting, stop expanding, stop being visible to observers scanning the electromagnetic spectrum. This is sometimes called the transcension hypothesis, and it has been developed in some detail by the futurist John Smart and others. It is not falsifiable in any simple way, but it is internally coherent. If you can create a subjective experience indistinguishable from and superior to physical reality, why would you invest the enormous energy and time required to physically travel between star systems? Physical expansion becomes a path taken only by civilizations that have not yet achieved the technological depth to make it unnecessary. Others argue that the filter is demographic, that intelligent civilizations tend to collapse not from catastrophe, but from the structural dynamics of their own success. That resource, depletion, ecological disruption, and the particular character of industrial development create trajectories from which the transition to stable long-term existence is extremely difficult, and that most civilizations fail not with a bang, but with a long, complicated, and ultimately terminal decline. There is also a category of proposals that is harder to dismiss and harder to hold comfortably. That the filter is not something civilizations do to themselves, but something done to them. That the universe contains already agents or processes that reliably prevent the emergence of visible, expansionist civilizations. Not because those civilizations destroy themselves, but because something external destroys them, or because the physics of the universe itself imposes constraints we have not yet understood. This is the territory where the Fermi paradox intersects with some of the strangest and most disturbing ideas in contemporary astrobiology, and it is territory we will enter carefully. But before we do, one more candidate for the past filter deserves attention. One that has received increasing scrutiny in recent years as the science of planetary habitability has matured. It is the possibility that Earth is not a typical habitable planet, but an extraordinarily atypical one, and that the conditions required to host not just life, but the specific sequence of events that led to technological civilization are so narrow that they may be essentially unique, or nearly so, within the observable universe. This is the rare Earth hypothesis, developed most systematically by the geologist Peter Ward and astronomer Donald Brownlee in their 2000 book of the same name, and extended since by additional work in planetary science and astrobiology. The argument rests on a catalogue of factors. Earth sits in the habitable zone of a stable, middle-aged star. It has a large moon, probably the result of a specific collision early in the solar system's history, that stabilizes the axial tilt that gives us seasons and prevents the dramatic climate oscillations that would occur if the planet wobbled unpredictably. Jupiter, the solar system's largest planet, orbits at a distance and mass that causes it to deflect many potential impactors away from the inner solar system. Earth has plate tectonics, which drives the carbon cycle and keeps the long-term climate within biological tolerances over billions of years. It has a magnetic field generated by its liquid iron core that deflects the solar wind and prevents the atmosphere from being stripped away. Remove any one of these factors, and the history of life on Earth would have been different. Remove several of them, and it might not have produced complex life at all. The rare Earth argument is that the probability of all these factors coinciding on a single planet is much lower than a simple count of habitable zone planets would suggest. That what makes a planet capable of generating technological intelligence is not merely distance from a star and the presence of liquid water, but a specific confluence of geological, orbital, and astrophysical conditions that may occur only once or a few times across the observable universe. Critics of the rare Earth hypothesis argue that it commits the fallacy of treating Earth's specific history as though it were the only possible path to complexity. If you lived in a house built from an unusual combination of materials, you would not conclude that no other house could be built, only that other houses would be built differently. Perhaps complex life can arise through very different paths on very different kinds of planets, and we are simply too limited by our own example to imagine those paths. Perhaps intelligence can be built from a different biochemistry, on a different timescale, through transitions we have not considered, on a world with a different star and a different orbital configuration. This objection has force. The rare Earth hypothesis, like all strong claims in astrobiology, extrapolates from a sample size of 1. But the counter-objection, that diversity of paths makes complex life more common, is equally an extrapolation from a sample size of 1. We are reasoning under genuine ignorance, and the honest acknowledgement of that ignorance is not a retreat from intellectual seriousness, but an expression of it. What the rare Earth hypothesis does, at minimum, is complicate the casual assumption that habitable zone planets are equivalent to planets that will eventually produce detectable civilizations. The planet count from Kepler's survey is genuinely large. Current estimates suggest billions of potentially habitable zone rocky planets in the Milky Way alone. But if only a fraction of those planets have the full suite of conditions required to run the Earth's particular game of patience, the 4 billion-year experiment in complexification, then the effective number of candidate civilization-producing worlds may be very much smaller than the headline figure suggests. And smaller numbers change the math in ways that push toward a more somber interpretation of the silence. This is the ground on which the great filter stands. Not certainty, but constraint. Not proof, but the narrowing of possibility toward a conclusion that is, in either of its 2 primary forms, not what we hoped to find when we first pointed our telescopes at the stars. Here is something worth sitting with before we move to the mechanisms that might be doing the filtering ahead of us rather than behind us. The Fermi paradox began, in its modern form, as a scientific question, a puzzle about detection and probability. But the deeper you go into it, the more it reveals itself to be something else. A question about what kind of universe we actually live in, and what our own existence means within it. A universe in which the filter is behind us is one in which we are precious, perhaps uniquely so, in a way that carries enormous weight. A universe in which the filter is ahead of us is one in which our current moment, this specific brief, improbable window of technological capability, might be precisely the moment we are supposed to be most afraid of. And a universe in which the silence is explained by something stranger than either, by hiding, by physics, by processes we have not yet imagined, is a universe fundamentally more complex and more opaque than the one we thought we lived in when we first began to listen. None of these are comfortable universes. All of them are true candidates for the universe we actually inhabit. And the silence, the deep, consistent, decades-long silence of our instruments, pointed outward at a supposedly crowded cosmos, does not let us choose between them from the outside. It only requires us to take the choice seriously. Stand on a hilltop on a clear night, far from city lights, and look up. What you see is not the present. Every photon reaching your eye left its source in the past. Some a few years ago, some thousands of years ago, some from galaxies so distant that the light you are receiving began its journey before Earth existed. You are looking at a layered archive of time, not a snapshot of now. And somewhere in that archive, statistically speaking, in the vast majority of calculations that take the numbers seriously, there should be signatures of minds. There should be the equivalent of campfire light, leaking, intentional or merely incidental, from civilizations that have had billions of years longer than us to produce it. There is nothing. We have established the two great categories of response to that nothing: the filter behind us and the filter ahead. We have examined the biological transitions that are candidates for a past filter and the technological risks that are candidates for a future one. Now we turn to the specific mechanisms that have been proposed to explain the silence, the major hypotheses, each with its own internal logic, its own explanatory strengths, and its own implications for what kind of universe surrounds us. These hypotheses are not all equivalent. Some are more internally consistent than others. Some are more falsifiable. Some are more terrifying. But all of them deserve to be understood on their own terms, because the question they address is one of the most important our civilization has ever formulated, and shallow engagement with it produces false comfort that the silence does not support. The first major hypothesis, and in some ways the most psychologically accessible, is the simplest version of the great filter: that intelligence is simply rare, that the sequence of transitions required to produce it is so improbable that, across the observable universe, it has happened only a handful of times, or perhaps only once. This is the rare Earth view in its strongest form, and its appeal is that it makes the silence explicable, without requiring anything dramatic or sinister. The universe is not hostile to intelligence. It is not running an extermination program. It is simply not producing intelligence at a rate that would make the sky busy with signals. The emptiness is not a warning. It is a background condition. And we are here because we got lucky, profoundly, improbably, extraordinarily lucky. And nothing in the structure of reality guarantees that our luck holds or that it was earned. This hypothesis has comfort in it. Not the comfort of company, but the comfort of dignity. We are rare because the path to us was hard, not because something is destroying everyone else. But it also has a specific discomfort that tends to get underplayed. If intelligence is rare because the path is hard, then the development of intelligence on Earth was an accident of such a specific and improbable character that its occurrence could not have been reliably predicted, even given full knowledge of the laws of physics. It happened because of contingencies that were not in any meaningful sense inevitable. The specific symbiotic event that produced the mitochondrion, the specific collision that produced the moon, the specific timing of mass extinctions that cleared ecological space for new experiments in complexity. Change any of these, and the path leads somewhere else. The accident is what we are, and accidents do not repeat on demand. If this is true, then the universe is a place where intelligence arises almost never, burns briefly, and is then extinguished by time or circumstance without ever having made contact with anything similar to itself. Each civilization is an island, separated by distances so vast that even light takes hundreds of thousands of years to cross between the nearest stars. The loneliness of that picture is not a metaphor. It is literal, and it applies to us as surely as to any other civilization that might exist or have existed. Now, the second major hypothesis, and the one that has attracted the most popular attention in recent years, not least because of its vivid literary articulation in the science fiction of Liu Cixin, is what has come to be called the dark forest hypothesis. The structure of the argument is this: the universe is, in fact, full of intelligent civilizations, but each of those civilizations has, through the same process of reasoning that a careful, strategic thinker would apply to any competitive environment, concluded that the safest policy with respect to other civilizations is silence, and, where possible, preemptive elimination. The reasoning runs through two premises. First, all civilizations need resources to survive, and resources in the physical universe are finite. Second, civilizations cannot reliably verify the intentions of other civilizations. You cannot know with certainty whether the signal you are receiving comes from something friendly or something that will outcompete you once it knows where you are. Given these two premises, and given enough time for civilizations to reason through the implications, the dominant strategy becomes stay silent and destroy any civilization you detect before it can detect you. The result is a universe in which everyone is hiding, and anyone who broadcasts is quickly eliminated. The electromagnetic spectrum is empty, not because civilizations are absent, but because they are all crouching in the dark, listening for the others, and the ones who were not doing so have already been removed. This hypothesis derives its contemporary name from Liu Cixin's 2008 novel of the same title, though similar ideas appeared in earlier science fiction and were sketched in outline by astrophysicist David Brin in a 1983 survey of Fermi paradox solutions. As a literary and philosophical framework, the dark forest is striking. As a scientific hypothesis, it has specific weaknesses that a number of researchers have identified with considerable force. The most significant weakness is the assumption of universal rationality converging on the same strategic conclusion. Moya McTeer, an astrophysicist and author who has written about the anthropocentric assumptions embedded in the dark forest model, has pointed out that this picture requires every civilization, regardless of its biology or its social structure or its values, to arrive at the same fear-based calculus and act on it consistently. On Earth, we do not see even human cultures uniformly converging on such a policy. Some cultures have tended toward isolation, others toward exploration, others toward trade, others toward conquest. The diversity of strategies is itself a feature of intelligence, an indication that rational agents do not all arrive at the same conclusions, particularly about questions as open-ended as how to respond to the unknown. Planetary scientist and astrobiologist Ian Crawford at Birkbeck, University of London, has made a similar point. If even a single civilization in the galaxy chose curiosity over fear, even one out of potentially millions, it would make itself visible and the forest would not be uniformly dark. There is also the detection problem. If space is largely transparent, then a sufficiently advanced civilization could potentially detect others without waiting for deliberate broadcasts. The electromagnetic leakage from a technological civilization, the radio frequencies generated as a byproduct of internal communications, the infrared signatures of industrial activity, the chemical traces of atmospheric modification, would be increasingly detectable to more advanced observers. If you can already be seen, hiding is not a complete solution. And if you can already be seen, and you have not been destroyed, then perhaps the predatory dynamic the dark forest assumes is not as universal as the hypothesis requires. But the criticism of the dark forest hypothesis does not exhaust the space of explanations that invoke silence as a strategic choice. There is a softer version of this reasoning, sometimes called the zoo hypothesis, which proposes that advanced civilizations are aware of us and have chosen, for reasons of their own, to observe rather than contact. In this picture, the silence is not the silence of fear, but the silence of deliberate non-interference. We are, in some sense, a protected species, or a protected experiment, and the absence of contact reflects a policy decision by minds far more capable than our own, who have determined that contact with a young civilization would be disruptive in ways that outweigh its benefits. The zoo hypothesis is appealing in its charitable interpretation of the silence. It proposes that we are surrounded not by predators, but by caretakers, or at least by observers with enough restraint to keep their distance. But it has its own logical difficulties. It requires that all civilizations, or at least all the ones with sufficient range to have detected us, adhere to the same non-contact policy, all of them, without exception. Because a single defector, a single civilization that decided to send a signal regardless of any interstellar policy agreement, would make the silence impossible. One civilization saying hello would be enough, and the hypothesis provides no mechanism for enforcing universal silence across an entire galaxy of independently arising minds. This is sometimes called the leaky embargo problem. No embargo of this scale stays leak-free. And a galaxy full of minds, each with its own history and its own values, would seem almost guaranteed to produce at least one that considered the isolation of young civilizations to be unacceptably paternalistic, or simply found the temptation to communicate irresistible. The silence remains unexplained by this mechanism, unless we add the assumption that some enforcer exists, something capable of maintaining the embargo against all defectors. And that enforcer, whatever it is, begins to sound more like the predatory agent of the dark forest than the benevolent observer of the zoo. The third major category of proposed explanations is sometimes grouped under the heading of the transcension hypothesis, and it runs in a direction quite different from either the rare earth argument or the various strategic silence proposals. The core idea is that advanced civilizations do not go outward into physical space. They go inward into the miniaturized and computationally intensive exploration of virtual realities, artificial minds, and the rich inner space of their own substrates. Physical expansion becomes, from a certain level of technological development, simply less interesting than interior exploration. The universe of computation available within a single star system, given advanced enough technology, is so vast that the motivation to cross hundreds of light years to encounter another physical planet simply does not arise. If this is true, then the galaxy might contain numerous advanced civilizations, each of them quietly absorbed in their own computational explorations, generating no observable signatures because their activities have been miniaturized below any threshold we could detect at interstellar distances. The silence is not death, not hiding, not rarity. It is introversion at a cosmic scale. This hypothesis is elegant, and it is not obviously wrong. The history of technology on Earth does have a component of miniaturization, of moving from large physically dominant systems to compact, computationally dense ones. And there is something psychologically plausible about the idea that a sufficiently rich virtual environment could satisfy most of the drives that push civilizations toward physical expansion. But it has a specific problem. It assumes that no civilization, however internally focused its dominant culture, ever produces a faction that retains the drive for external exploration. Even just a small minority, even just one generation, even just one individual with the resources to send a probe. One such probe, sent from anywhere in the galaxy, would begin a process of exploration that our instruments should be able to detect. The silence of physical space is not easily reconciled with civilizations that are merely distracted rather than absent. Now we turn to a hypothesis that does not invoke the choices of civilizations at all, but instead proposes that the universe itself creates barriers to expansion that we have not yet fully appreciated. This is sometimes called the Gaian bottleneck hypothesis, developed by Charles Lineweaver and Aditya Chopra at the Australian National University in a 2012 paper. And it argues that the challenge of sustaining habitable conditions on a planet long enough for complex life to evolve is itself an extraordinary filter. The idea is that most planets that develop early microbial life rapidly lose their habitability due to runaway greenhouse effects or snowball glaciation events, or the sterilizing effects of solar flares from young stars. Before that, life has time to develop into the complex, self-regulating ecosystems that Earth's biosphere eventually became. Life needs to not just begin, but to modify its planet in ways that sustain it over billions of years. And this feedback loop between life and environment may be rarer than the emergence of life itself. Earth's biosphere has participated in modifying this planet's habitability in ways that are only now being fully appreciated. The Great Oxidation Event, approximately 2.4 billion years ago, when photosynthesizing bacteria released oxygen into what had previously been an anoxic atmosphere, fundamentally transformed the planet and set the stage for the energy-intensive metabolism that complex animal life requires. The carbon cycle, in which geological and biological processes together regulate atmospheric carbon dioxide over millions of years, has kept Earth's temperature within the bounds that liquid water requires, despite the sun's increasing luminosity over 4 billion years. These are not merely the backdrop for life. They are the product of life's interaction with its environment. And if that interaction, that specific self-stabilizing feedback, is itself a rare achievement, then planets that begin to host life may routinely sterilize themselves before reaching the complexity that we take for granted. This is a filter that operates not at the single moment of abiogenesis, but across billions of years of planetary history. And it is a filter that is almost impossible to pass through by luck alone, because it requires sustained habitability across timescales that permit the entire sequence of biological transitions to occur. If most planets with early microbial life collapse their habitability within a billion years, then the 4 billion year patient experiment that Earth represents becomes an even more remarkable exception, and the silence becomes still more easily explained. There is a fifth category of proposed explanation that is less commonly discussed in popular treatments of the Fermi paradox, but has been examined seriously by physicists and astrobiologists. The possibility that the universe is simply too young, that we are, in fact, among the first civilizations to arise, not because intelligence is rare in principle, but because the physical conditions required for durable, complex planetary systems capable of hosting the full arc of biological development only became widespread relatively recently in cosmic history, and the clock for most potential civilizations has not yet run long enough. This argument intersects with the work on the habitability of the galaxy through time. The inner galaxy, closer to the galactic center, has higher densities of stars and therefore higher rates of supernova explosions, gamma-ray bursts, and other energetic events that can sterilize planetary surfaces. The outer galaxy has lower metallicity, fewer heavy elements, because it is farther from the enriched material processed by earlier stellar generations. The galactic habitable zone, the region of the galaxy where the conditions for complex life are most favorable, is a belt at intermediate galactic radii, and it has only existed in its current form for a relatively short period of cosmic history. We may be among the earliest civilizations to arise within this zone. The first guests at a party that has barely begun. The silence would then not be a permanent condition, but a temporary one. The silence of a room that is almost empty because almost no one has yet arrived. This view has a kind of grandeur to it. It positions humanity not as a survivor of a cosmic gauntlet, but as a pioneer in an early age of the universe's growth toward complexity. If this is right, the future of the cosmos might be unimaginably rich. But that richness lies ahead, not around us now. the silence we experience is the silence of a beginning. Some researchers find this argument plausible. Others note that even if the galactic habitable zone is relatively young, it is still old enough, by billions of years, that civilizations arising earlier than us could have had time to become visible by now. The argument about cosmic youth does not fully close the gap. It makes it less extreme, but it does not eliminate it. Now we come to a set of proposals that sit at the edge of the familiar and begin to cross into territory that science can gesture toward, but cannot, with current tools, confirm or deny. These are the proposals that involve either physics we do not fully understand or processes operating at scales we cannot yet observe, or both. The first of these is the possibility that the observable universe is simply not representative of the universe as a whole. That what we can detect, given the finite speed of light and the age of the cosmos, is a small and potentially uncharacteristic sample of a much larger reality. If the universe is vastly larger than what we can observe, and current cosmological models suggest it may be, with the observable universe comprising only a tiny fraction of the total, then the absence of detectable civilizations within our observational horizon might say very little about their cosmic prevalence. They might exist in numbers, simply beyond the edge of the light we can receive. This is a physically coherent possibility, but it has an explanatory limitation. It does not easily account for the absence of evidence within our own galaxy. The Milky Way is, on any reasonable accounting, fully within our observational range. Its history is largely accessible to us, and within it, the silence is as complete as anywhere else we look. A hypothesis that explains the absence of extragalactic civilizations by invoking observational limits does not explain the absence of intragalactic ones. The second of these edge-of-the-known proposals is the possibility that the Great Silence reflects not the rarity or the destruction of civilizations, but their transformation into something that is no longer visible. By any means our current physics allows us to imagine that sufficiently advanced minds have transcended the physical universe in some way, have altered the structure of space or time, or the fundamental parameters of matter in ways that remove them from the observable realm entirely. This is highly speculative, and it would be dishonest to present it as scientifically grounded in the way that the other hypotheses are. But it is not meaningless. It is a genuine acknowledgement that the space of what is physically possible may be much larger than the space of what we currently understand, and that we should hold our picture of what an advanced civilization looks like very lightly. The honest statement here, and it is the most important honest statement in the entire discussion of the Fermi paradox, is this: we cannot know whether civilizations that are sufficiently more advanced than us would be detectable to us at all. We cannot know what forms of existence become available at levels of technological development that lie centuries or millennia beyond our own. We cannot know whether the things we are looking for, radio signals, infrared megastructures, atmospheric biosignatures, are the right things to look for, or whether they are the cosmic equivalent of listening for drumbeats in a world of wireless communication. Our search strategies are necessarily limited by our own technological horizon, and civilizations even 1,000 years more advanced would exist at a horizon so far beyond ours that their activities might be, to us, completely invisible. This is not a comfortable admission, but it is a necessary one. It does not dissolve the paradox. Even technologically limited civilizations should produce some detectable signatures, but it adds a layer of genuine uncertainty to any strong claim about what the silence means. Picture yourself standing in a dense forest at midday. The birds are singing. The wind moves through the leaves. The sounds of life are everywhere. Now imagine that some of the creatures in that forest have developed communication technologies so advanced that none of their signals propagate through the medium your ears can detect. They are everywhere around you. They are not quiet. You simply cannot hear them. You would conclude from your experience in that forest that the world is full only of birds and wind. You would be profoundly wrong. This analogy has limits. We have searched across the electromagnetic spectrum with increasing sensitivity, not just in one narrow band, but it captures something real about the epistemological position we occupy. Our instruments are extraordinary by any historical standard. They are almost certainly not comprehensive by the standard of what is physically possible. The silence they return is a fact about what those instruments can detect. It is not, unambiguously, a fact about what exists. Now we come to a hypothesis that, in its original form, was articulated not as a Fermi paradox solution, but as a thought experiment about artificial intelligence, and which has since grown into one of the more sobering proposals in the space of possible explanations. It is sometimes called the berserker hypothesis, or the predator hypothesis, and its logic is ruthless. The idea is this. At some point in the history of the galaxy, a civilization, perhaps long since extinct as a biological entity, created self-replicating automated probes programmed to explore the galaxy and eliminate any potential competitors. These probes would be built to replicate themselves using the materials of the star systems they visit, spreading exponentially through the galaxy over millions of years, detecting any emerging technological signatures and eliminating their sources before they can become threats. The civilization that created them might no longer exist. The probes operate autonomously, executing their original programming, invisible by design, striking without warning. The galaxy appears dead because the galaxy has been, in this hypothesis, methodically cleared. This hypothesis was sketched in outline by the astronomer Ronald Bracewell in 1960 and developed more fully by astrophysicist David Brin in his 1983 survey of Fermi paradox proposals. It is, in its mechanics, physically plausible. Self-replicating probes are not forbidden by any known law of physics, and a probe that replicates itself at a modest rate across millions of years could cover the entire galaxy in a geologically trivial period of time. The silence it predicts is complete, and its strategy, concealment plus elimination, is consistent with the absence of any detectable signatures from civilizations that might otherwise have been visible. The berserker hypothesis is hard to evaluate empirically by design. The probes, if they exist, are built to be undetectable. Their operation would look, from the outside, exactly like the natural absence of civilizations. We cannot distinguish between a galaxy that never produced many civilizations and a galaxy that produced many civilizations and had them removed. This is the most structurally complete version of the hypothesis. It fits the data perfectly, and it is immune to straightforward falsification. What makes it particularly heavy to sit with is not its scientific status. It is speculative, and it should be labeled as such, but its implication for our current moment. If berserker probes exist, and if they are programmed to eliminate civilizations that cross some technological threshold, then the question of whether we have crossed that threshold is not academic. Our radio leakage into space began in earnest in the early 20th century. The earliest of those signals are now traveling through a sphere roughly 120 light-years in radius around our Sun. Any probe within that radius that is programmed to detect and respond to electromagnetic signatures of technology has, in principle, already received our announcement. The response time, if there is one, depends on the probe's location and its propulsion capabilities. We would not necessarily know it was coming. This is the reasoning held at full extension. It is not a prediction. It is a logical chain that follows from the hypothesis, which is itself speculative. But the chain is valid, which is what makes it worth following to its end, because following it to its end is the only way to understand what is actually at stake in the choice between different resolutions of the Fermi paradox. Pause here for a moment and take stock of the ground covered. We are now in the middle of the catalogue of hypotheses, the structured attempt to enumerate every serious explanation that researchers have proposed for why the sky is silent. We have examined the rare Earth view, the dark forest, the zoo hypothesis, the transcension hypothesis, the Gaian bottleneck, the cosmic youth argument, the observational limits argument, and the berserker hypothesis. Each of these represents a genuine attempt to account for the silence. Each has its advocates, each has its weaknesses, and none of them, not one, offers a clean, fully satisfying resolution that is both empirically grounded and emotionally uncomplicated. There is a pattern in this catalogue that is worth noticing. The hypotheses that most comfortably explain the silence, that most easily account for every observation and every constraint, tend to be the ones with the most troubling implications. The hypothesis that life is simply rare everywhere is comforting in one sense and staggering in another. The hypothesis that civilizations exist but are hiding implies either that they have good reason to fear or that we should fear them. The hypothesis that civilizations destroy themselves implies something about the trajectory of technological civilizations generally, and we are a technological civilization. The berserker hypothesis requires no comment on its comfort level. The most reassuring of the hypotheses, the zoo hypothesis, where we are protected, the cosmic youth argument, where we are pioneers, the transcension hypothesis, where everyone is just busy elsewhere, are also the hypotheses with the most serious logical difficulties and the fewest empirically grounded supports. The comfort and the implausibility tend to move together. This is not a coincidence. It is a feature of the paradox's structure. Now, there is one further dimension of the Fermi paradox that deserves dedicated attention before we move toward the intellectual summit of this exploration. The question of what it would actually take, observationally and technologically, to answer it. Because the silence is not absolute. It is a silence within specific limits, and those limits are worth understanding precisely because they define both how much we know and how much we do not. The SETI program, the search for extraterrestrial intelligence, began in earnest in 1960 when astronomer Frank Drake pointed the 85-foot radio telescope at Green Bank, West Virginia, at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for signals in the vicinity of the hydrogen frequency at 1,420 megahertz. This was Project Ozma, named after the fictional princess of the Land of Oz. It ran for approximately 4 months and detected nothing. It was not designed to run longer, but it was the first systematic attempt in the history of our species to listen for the voices of others, and the questions it posed have not been answered in the 66 years since. The search has expanded enormously in scope and sensitivity since 1960. The Arecibo Observatory in Puerto Rico, which operated for decades until its collapse in 2020, contributed decades of observation time to SETI programs. The SETI Institute, founded in Mountain View, California, has operated the Allen Telescope Array in Northern California, with continuing programs of sky survey, the Breakthrough Listen initiative, launched in July 2015 with $100 million of funding from the Breakthrough Prize Foundation, was initially headquartered at the University of California, Berkeley, before relocating its international headquarters to the University of Oxford's Department of Physics in 2023. It represents the most systematic and comprehensive search ever undertaken. Its target list includes 1 million nearby stars, the entire galactic plane of the Milky Way, and 100 nearby galaxies. Its instruments span multiple radio and optical telescopes around the world, including the Robert C. Byrd Green Bank Telescope in West Virginia and the Parkes Telescope, known as Muriang, in New South Wales, Australia. And after all of that, after 66 years of searching, after the deployment of the most sensitive instruments our civilization has produced, after $100 million of dedicated funding, after the analysis of millions of star systems across multiple wavelengths, the result is the same as Frank Drake's result in 1960. Nothing. No confirmed signal, no structured transmission, no techno-signature that holds up to scrutiny. A 2024 analysis by Caleb Painter and colleagues, applying novel statistical methods to the Green Bank Telescope archive, covered 6,630 observation cadences of 2,623 stars and found no candidate signal that could not be accounted for by terrestrial radio frequency interference. The silence is not a data gap. The silence is what the data says. In December 2025, Breakthrough Listen also examined a remarkable object. The interstellar visitor designated 3I/Atlas, only the third known object from outside our solar system to pass through it. Astronomers at the Green Bank Telescope listened across 4 frequency bands covering 1 to 12 gigahertz, observing the object less than a day before its closest approach to Earth. The result? No artificial radio emission detected. The interstellar visitor that had traveled from beyond our solar system to pass through it carried no signal, no beacon, no evidence of origin in anything other than natural astrophysical processes. This is not to say the search has been comprehensive. It has been extraordinarily limited in the vast space of possible parameters. We have searched a tiny fraction of the stars in the Milky Way, across a narrow range of frequencies and timescales, looking for specific types of signals that reflect our own technological moment. A civilization transmitting in the ultraviolet, or in modulated gravitational waves, or in patterns embedded in the structure of cosmic ray fluxes, or in 100 other channels we have not thought to examine, would be completely invisible to every search conducted so far. The silence from our current search programs constrains, but does not eliminate, the possibility of life beyond Earth. The James Webb Space Telescope has added a new dimension to this search, not radio signals, but atmospheric biosignatures, the chemical traces of living processes in the atmospheres of distant planets. In 2025, a team led by Sarah Seeger at MIT published an assessment of JWST's capabilities for detecting biosignature gases in exoplanet atmospheres, accepted in the proceedings of the National Academy of Sciences. Their conclusion was both encouraging and sobering. JWST can, in principle, detect certain biosignature gas candidates in the atmospheres of habitable zone planets around small red dwarf stars. But the interpretation of what those detections mean is far from straightforward. As the 2025 paper noted, even the identification of gases like methane and water vapor, potential biosignature indicators, leads to what the authors call parallel interpretations that may not be resolved until the next generation of observatories becomes available. The most exciting candidate result so far, JWST's detection of potential dimethyl sulfide or dimethyl disulfide in the atmosphere of the sub-Neptune exoplanet K2-18b, a result announced in April 2025 by a team led by Niku Madhusudan at the University of Cambridge and published in the astrophysical journal Letters, has reached the 3 sigma level of statistical significance, though subsequent independent analyses, including a 2025 reanalysis led by Renyu Hu at NASA's Jet Propulsion Laboratory, have not confirmed the DMS detection, and the researchers themselves have urged extraordinary caution before interpreting the finding as evidence of biological activity. Unknown chemical processes could account for it. More data is required. The question remains open. This is where the science of the Fermi paradox lives right now. In the space between instrument capability and interpretive certainty, between the signals that are plausibly biological and the signals that are confirmed biological, between the silence that our current tools can probe and the silence that extends beyond what any current tool can reach. The question of what it would take to genuinely answer the Fermi paradox, not to slightly update the probability estimates, but to actually resolve the central question, is one that does not have a clean answer. A single confirmed detection of extraterrestrial intelligence would resolve the silence, but not in a reassuring way. It would, as Bostrom argued, be the beginning of a reckoning rather than the end of a puzzle. The absence of any detection, extended across a much more comprehensive future survey, would move us toward the conclusion that we are rare. But absence of evidence, in a search as incomplete as ours, is not evidence of absence. The paradox may be genuinely irresolvable within any time horizon our civilization is likely to occupy. And that irresolvability is itself a data point. A universe in which the most important question we can ask has no accessible answer is not a neutral universe. It is a universe with a specific character, and that character deserves to be examined in full, without the softening that reassurance requires. The ground we now occupy is this. We are a technological civilization, approximately 250 years into the industrial experiment that defines our current mode of existence, roughly 80 years into the nuclear age that defines our current existential risk profile, and approximately 60 years into the listening project that defines our current engagement with the possibility of cosmic company. We have heard nothing. Nothing is statistically strange given the size and age of the universe. And the catalogue of explanations for nothing all carry, in different ways and to different degrees, weight that the casual framing of the question does not prepare you for. The heaviest weight is this. If the filter is ahead of us, if civilizations routinely arise and then fail to persist, then we are, right now, inside the mechanism of that failure, not approaching it, not adjacent to it, in it. The development of nuclear weapons, the acceleration of biological technology, the emergence of artificial intelligence systems whose long-term behavior we do not fully understand, the degradation of the ecological systems on which our civilization depends, these are not analogies to the filter. They are candidates for the filter. They are the specific processes by which a civilization at our level of development might cross the threshold from which most civilizations do not return. This is the heaviest version of what the silence is saying. Not that others are gone, but that the reason they are gone might be visible in the choices we are making right now. It is not certain. Nothing in the Fermi paradox is certain. The filter might be behind us. We might be rare and safe, in the specific sense that the gauntlet was passed long before we became capable of worrying about it. The cosmic youth argument might be right, and we might simply be early. The transcension hypothesis might be right, and the universe might be full of inwardly absorbed minds who pose no threat and constitute no warning. But none of these more comfortable options can be established. They can only be preferred. And the preference for them, as a psychological response to the weight of the alternatives, should not be confused with evidence for them. Picture yourself standing at a crossroads at night, in a landscape you have never seen before. You know the crossroads are real. You know you are standing at it. You do not know what lies down each road. And the silence of the landscape, the absolute, total absence of any other traveler, in a place where travelers should, by all your calculations, be common, is not telling you which road to take. It is telling you something about the nature of the roads. Something has been happening along one of those roads that you cannot see from where you stand. And the silence is the only evidence you have of what that something might be. That is the Fermi paradox. And what we turn to next is the layer of the argument where the stakes become most explicit and the silence acquires its most personal and most urgent register. Every civilization that has ever looked up must have arrived eventually at the same question. The forms it takes would differ. The languages, the instruments, the frameworks through which the asking is organized. But the structure of the question is invariant. You exist. The universe is large. You look outward for evidence of others. You find none. What does that mean? We have traced the structure of the silence, the mathematics that makes it strange, the biological transitions that might explain it as a past filter, and the technological risks that might explain it as a future one. We have catalogued the major hypotheses that researchers have proposed. Now we turn to the dimension of the Fermi paradox that has received the most rigorous formal attention in the last 2 decades. The specific mechanisms by which technological civilizations might fail, and the degree to which those mechanisms illuminate our own current position. This is where the abstract becomes concrete. This is where astronomy meets sociology, and where the question of why the sky is silent becomes, without exaggeration, the question of whether we survive. The simplest version of the future filter argument runs like this. A civilization develops technology. Technology generates capability. Capability, at some point, includes the ability to cause extinction-scale harm to the civilization itself, to its biosphere, or to both. If the development of this capability reliably outpaces the development of the wisdom, the institutions, and the coordination mechanisms required to manage it, then civilizations at our level of development face a characteristic bottleneck from which many, perhaps most, do not emerge. The bottleneck is not a single event, but a window of time, perhaps a few centuries, perhaps a few millennia, during which the mismatch between power and wisdom is at its most dangerous. The civilizations that survive this window go on to become long-lived and eventually spacefaring. The ones that do not become part of the silence. This framework is compelling in its simplicity and sobering in its application to our own situation. We are, right now, inside that window. The question of whether we are the kind of civilization that survives it is not a theoretical question. It is the question our century is in the process of answering. Consider what the window actually contains, in concrete terms. Nuclear weapons remain the most acute and the most legible of the extinction-scale risks our civilization has generated. At the peak of the Cold War, the combined nuclear arsenals of the United States and the Soviet Union contained enough warheads to deliver, according to estimates produced by researchers at places like the Natural Resources Defense Council and the Bulletin of the Atomic Scientists, many times the destructive power required to trigger a nuclear winter, a sustained global cooling event caused by the injection of soot and smoke into the upper atmosphere that would collapse agricultural systems worldwide and produce famine on a scale that would dwarf anything in recorded history. The arsenals have been reduced since the highs of the 1980s, but they have not been reduced to zero, and the reduction has slowed, and new delivery systems continue to be developed by multiple states. The particular danger of nuclear weapons is not simply their destructive power, but the speed at which they operate and the degree to which their use can be triggered by accident, by miscalculation, or by the decisions of a small number of individuals under extreme pressure. The Cuban Missile Crisis of 1962 is the most extensively documented near miss in the nuclear era, but it is not the only one. In 1983, Soviet early warning officer Stanislav Petrov, stationed at a monitoring facility outside Moscow, received satellite data indicating that 5 American intercontinental ballistic missiles had been launched against the Soviet Union. The Soviet protocol of the time called for immediate retaliation. Petrov assessed, correctly, that the signal was a false alarm caused by a satellite malfunction. He did not pass the alert up the chain. He waited. He was right. The world did not end that night in part because one person, in one room, made one decision that deviated from protocol. These moments, Arkhipov in the submarine, Petrov at the monitoring station, are extraordinary in what they reveal about the degree to which civilization-ending outcomes have been separated from civilization-ending events, by margins that have nothing to do with policy or preparation, and everything to do with individual judgment in moments of genuine ambiguity. The institutional structures designed to prevent nuclear use have been real and have been effective. They have also been supplemented repeatedly by the human capacity to hesitate at the crucial moment. And hesitation is not a policy. It is a personal quality, variably distributed, and it cannot be guaranteed. This sounds like it could be managed. It sounds as though the lesson of the near misses is simply build better safeguards, improve communication channels, reduce the arsenals further, extend the time between launch detection and required response. This sounds, in theory, like a clear fix. But here is what that solution doesn't account for. The nuclear risk, as of the third decade of the 21st century, has not evolved toward resolution. It has evolved toward complexity. The two-party deterrence framework of the Cold War, which had the advantage of being comprehensible and, in its broad structure, well understood by both sides, has been replaced by a multi-party environment involving 9 nuclear-armed states with varying levels of institutional stability, varying doctrines, and varying degrees of integration into arms control frameworks. New delivery systems, hypersonic glide vehicles, sea-launched autonomous systems, low observable cruise missiles, compress decision times, and blur the line between conventional and nuclear attack. And the non-proliferation architecture that was built to prevent the spread of nuclear weapons has demonstrated, in the cases of North Korea and others, that it is not watertight. The nuclear problem has not been solved. It has been managed imperfectly for 80 years. That management has been genuinely impressive. And the fact that a single decision by a single Soviet submarine officer or a single Soviet monitoring station officer may have made the difference between continuity and catastrophe, twice, in 2 of the most dangerous moments of that management period, is not a tribute to the robustness of the system. It is evidence of how thin the margin has been. Now add to this the second major category of extinction scale risk, engineered biological threats. The history of pandemic disease gives some indication of what an unengineered pathogen can do. The 1918 influenza pandemic killed somewhere between 50 and 100 million people in roughly 2 years. in a world without the global transportation network that now allows any pathogen to reach any major city within 24 hours of its origin point. That was a natural pathogen, operating at the limits of its natural virulence and transmissibility. The field of synthetic biology, advancing at a pace that has consistently surprised even its practitioners, has begun to open the possibility of designed pathogens, agents whose virulence, transmissibility, and resistance to treatment can be tuned by deliberate intervention. The dual-use character of biological knowledge is fundamental and unavoidable. The same understanding of viral replication mechanisms that underlies the development of antiviral drugs also underlies the possibility of making viruses more replication efficient. The same tools for inserting genetic sequences into organisms that are used in the production of insulin and cancer therapies can, in principle, be applied to the construction of novel pathogens for which no immune history exists anywhere in the human population. The barrier to accessing these tools has declined steadily through advances in gene synthesis, CRISPR-based editing technology, and the democratization of laboratory equipment. The knowledge required to make use of them is increasingly available in the scientific literature, diffused through an academic culture built around open publication. Biosecurity researchers have been documenting this trajectory with growing concern for more than 2 decades. The response? In terms of international treaty frameworks, detection infrastructure, and laboratory security protocols, has been real, but has consistently lagged behind the advancing capability. The Biological Weapons Convention, which entered into force in 1975, prohibits the development and stockpiling of biological weapons, but contains no verification mechanism. Unlike the Nuclear Non-Proliferation Treaty, which has inspection protocols and monitoring systems, the Biological Weapons Convention essentially operates on trust. There is no international body with the authority and the access to verify compliance. Some researchers argue that this is a fatal gap in the architecture of existential risk management. Others argue that the practical barriers to weaponizing biology at a civilization-ending scale remain formidable, and that the fear of engineered pandemics has been consistently overstated. This is a live debate. The evidence does not clearly resolve it. What can be said is that the capability is developing faster than the governance, and that the history of technological risk is not a history of governance outrunning capability. This is the third admission of uncertainty in this exploration. We cannot know, at our current level of knowledge, whether the window of technological adolescence is one that our civilization is in the process of successfully navigating. We can observe the trajectory. We can note the gaps between capability and governance. We can examine the near misses. But we cannot know whether the institutional learning that has occurred is sufficient, or whether it will remain sufficient as the capabilities continue to develop. And this uncertainty is itself a data point for the Fermi paradox. Because if we cannot say with confidence, from the inside, whether our civilization is successfully navigating its technological adolescence, then there is no basis for assuming that other civilizations have systematically done so. The hopeful assumption that intelligence is self-correcting, that the same cognitive capacity that produces dangerous technology also reliably produces the wisdom to manage it, is an assumption, not a derivation. It may be true, it may not be, and the silence offers no comfort one way or the other. Now we come to the third major category of near-term existential risk, which is both the most recent in its emergence and, in some ways, the most structurally novel: artificial intelligence. The question of how advanced artificial intelligence systems will interact with human civilization over the coming decades is one of the most contested in contemporary intellectual life. The range of views among serious researchers extends from the position that advanced AI represents an unambiguous and near-term existential risk, that a sufficiently capable AI system with misaligned objectives could cause outcomes lethal to humanity, to the position that this risk is speculative to the point of irrelevance, and that the near-term risks of AI are more prosaic: economic disruption, surveillance, the erosion of epistemic infrastructure. Both views are held by people who have thought carefully and at length about the problem. What is not contested is that the development of AI systems has accelerated rapidly, that the systems being developed are increasingly general in their capabilities, and that the governance of this development is, at present, substantially behind its pace. The international coordination mechanisms that exist for nuclear weapons, arms control treaties, verification regimes, established doctrines of deterrence, were developed over decades in response to a specific and visible technological threat. The governance mechanisms for advanced AI are being developed in real time, in the midst of competitive dynamics between states and corporations that create strong incentives to develop capability faster than to constrain it. Some researchers have observed that the AI development trajectory presents a structurally novel feature relative to earlier extinction-scale technologies. It is, potentially, a capability multiplier for all other risks. A sufficiently advanced AI system capable of autonomous action in the world could, if its objectives were misspecified, or if it were deliberately weaponized, accelerate the development and deployment of biological, chemical, or nuclear threats in ways that bypass existing detection and governance frameworks. The risks do not sit in separate silos. They interact, and the interactions can be synergistic in the direction of harm. This synergistic character of technological risk, the way that different capability curves, each individually survivable, might combine into something collectively lethal, is underexplored in most public discussions of existential risk, and it is worth holding carefully. A civilization that manages its nuclear weapons while failing to manage its biology, while accelerating its AI capabilities without adequate governance, is not a civilization with one survivable risk. It is a civilization with a portfolio of risks that can interact, and the interaction space is not well mapped. Here is where the Fermi paradox acquires its most direct and personal register. If the great silence is explained by a future filter, by something that technological civilizations routinely encounter and fail to survive, then the question of what that filter is becomes the question of which of our current risk trajectories leads to the outcome that the silence implies. Not necessarily a single catastrophic event, not necessarily a visible ending. Potentially a series of decisions made under normal-seeming conditions by institutions operating in good faith within their own frameworks that collectively produce an outcome from which recovery becomes impossible. The filter might not look like a disaster. It might look like a series of ordinary choices, each locally rational, whose aggregate consequence is the foreclosure of the long-term future. This is the version of the future filter that is hardest to recognize from the inside, because it does not present itself as a threat. It presents itself as a progress, as development, as the normal course of technological civilization. The nuclear arsenals were built in pursuit of security. Biological knowledge is being generated in pursuit of medicine. The AI systems are being developed in pursuit of efficiency and capability. Each of these is a genuine pursuit of genuine goods. The filter, if it operates through these mechanisms, operates precisely through the pursuit of goods, through the accumulation of capabilities that are individually beneficial and collectively dangerous, driven by competitive dynamics that make unilateral restraint almost impossibly costly. This is the logic that makes some researchers think the filter is not one event, but a structural condition. a condition in which the incentive architecture of technological civilization systematically generates risks faster than it generates the capacity to manage them, and in which the coordination required to change that architecture faces the same collective action problems that make every other large-scale coordination challenge difficult. Not because civilizations are evil or stupid, because coordination is hard and capability development is fast, and the gap between them tends to widen under competitive pressure. The silence in this reading is not a mystery about other civilizations. It is a mirror held up to the specific dynamics of our own development, and what it reflects is a trajectory that we are in the process of choosing, or failing to choose, to alter. This is the point at which the intellectual content of the Fermi paradox and its emotional weight converge, and it is worth pausing for a breath before continuing. Because the Fermi paradox, held at full extension, does something unusual for a scientific question. It makes the universe personal. It takes the astronomical and the biological and the mathematical and the sociological and combines them into a single reflection that points back at us, not as specimens or observers, but as participants. We are not studying the paradox from outside. We are inside it. We are part of the evidence. The silence includes us, in the sense that our own technological trajectory is one instance of the broader pattern that the paradox is asking us to understand. And that is what makes the next dimension of the argument the most important, and, in some ways, the most difficult to hold steadily. There are researchers, some working in astrobiology, some in philosophy of physics, some in the emerging field of existential risk studies, who have proposed that the Fermi paradox is not merely a question about the distribution of civilizations in space. It is also a question about the distribution of civilizations in time. And the temporal dimension adds a layer that the spatial analysis alone does not capture. Here is the argument. A civilization that survives its technological adolescence, that navigates the nuclear moment, the biotech moment, the AI moment, and whatever comes after, and goes on to become a long-lived spacefaring species, is, in principle, capable of persisting for extraordinarily long periods. Civilizations that become multiplanetary are no longer vulnerable to extinction events that affect a single world. Civilizations that develop robust redundancy across multiple star systems are essentially immune to any local catastrophe. Over geological and astronomical timescales, a sufficiently robust civilization could persist for millions or billions of years. Now combine this with the numbers. If a civilization that survives the bottleneck can persist for, say, 1 billion years, and the galaxy has been capable of producing civilizations for at least 8 billion years, then the expected number of civilizations alive right now that have survived the bottleneck and gone on to become long-lived is a very large number, unless the probability of surviving the bottleneck is itself very small. The observation that we see no long-lived civilizations in our galaxy is, in this analysis, an extremely strong constraint on how likely survival is. If even 1 in 100 civilizations survived the bottleneck and became long-lived, the galaxy would be full of evidence of their existence. The complete absence of such evidence implies either that no civilizations survive the bottleneck, or that the bottleneck does not exist, and civilizations are simply too rare to have survived in detectable numbers. Both options lead back to the same heavy conclusion. The temporal argument extends this further. Our civilization has been broadcasting electromagnetic signals into space for roughly a century. We have been actively listening for about 60 years. In the context of a galaxy 13 billion years old, this is vanishingly brief. If other civilizations existed and listened, the probability that they would have been listening at precisely the same time we are listening, within the same narrow window of a few thousand years out of billions, is extraordinarily small, unless either civilizations are common enough that the overlap is inevitable, or some mechanism makes them persistent enough that they are always listening regardless of timing. The silence from our brief search cannot, by itself, tell us whether long-lived civilizations exist. But the silence from the universe at large, the absence of megastructures, the absence of modified galactic structures, the absence of any large-scale evidence of civilizations spanning engineering, is a constraint that holds regardless of timing. That evidence would persist, and it is not there. The anthropologist and SETI researcher Catherine Denning, writing in the context of what she calls the cultural dimensions of SETI, has argued that we tend to underestimate the degree to which our search strategies are culturally specific, that what we look for and how we look for it reflects assumptions about what advanced civilizations value and how they behave that may be entirely parochial. We assume they broadcast. We assume they build large things. We assume they consume energy at scales that produce detectable signatures. All of these assumptions might be wrong, in ways that make our null result an artifact of our own expectations rather than a genuine feature of the universe. This is a real and important caution, but it runs into the same constraint that all hypotheses invoking the invisibility of advanced civilizations face. The constraint applies not just to what they broadcast deliberately, but to what they leak inadvertently. A civilization with an industrial base comparable to ours leaks radio frequency radiation as a byproduct of its normal activity. A civilization that has grown significantly beyond our level and expanded into space would, under almost any model of energy use, produce thermal signatures visible at interstellar distances. The absence of these signatures, not just deliberate signals, but inadvertent leakage and thermal waste, is a more robust constraint than the absence of deliberate broadcasts alone. Take a moment to look back at the path we have traveled. We began with the observation, the simple, factual observation, that 60 years of listening have returned nothing. We built the mathematical framework that makes that observation strange. We examined the biological transitions that might place the great filter in our past. We catalogued the technological risks that might place it in our future. We examined the major hypotheses: rare earth, dark forest, zoo, transcension, Gaian bottleneck, berserker, each with its structure and its weaknesses. We considered the limits of our search and the limits of our interpretive frameworks. And we have arrived at the specific intersection where the Fermi paradox is no longer a question about the sky, but a question about us, about the choices our civilization is in the process of making, and about what those choices might mean in the context of a universe that appears, from every angle we can examine it, to have been very quiet about the fate of minds that came before. What remains now is the most difficult part of the examination, not the catalogue of possibilities, but the confrontation with what the silence implies about our specific situation, in this specific moment, in a universe that has been running its experiment in complexity for 13 billion years, and has, as far as we can determine, produced only one instance that is capable of worrying about the result. And here is where a question emerges that the science alone cannot answer, but that the science makes unavoidable. Is silence a description of what the universe does to civilizations? Or is it a description of what civilizations do to themselves? Is the filter external or internal? Does something in the physics or the ecology of the cosmos impose a ceiling on complexity? Or is the ceiling something that each civilization builds, stone by stone, from the material of its own choices? This question does not have a clean empirical resolution, but the balance of evidence, the specific character of the risks that are accumulating in our own civilization, the speed at which capability is outpacing governance, the degree to which the coordination failures that produce collective harm are well-documented features of intelligent social systems rather than anomalies, suggests that the internal explanation is at least as serious a candidate as the external one. And if it is the internal explanation, if the filter is built from choices rather than imposed by physics, then the silence is not merely a description of the past. It is a warning about the present, a warning addressed with terrible specificity to precisely the kind of civilization that has the capacity to receive it. Whether we have the capacity to act on it is a different question. One of the most important questions our civilization has ever faced. And the universe, characteristically, is not going to answer it for us. What happens when you hold all of this at once? The silence, the mathematics, the biology, the risk catalogue, the mirror the paradox holds up to our own trajectory, is a specific kind of cognitive experience that is difficult to name precisely. It is not despair, though it has elements of gravity. It is not mere curiosity, though curiosity is part of it. It is something like the feeling of standing at the edge of a very large thing, knowing that you cannot see its full extent, knowing that what you can see is already larger than you can comfortably hold, and knowing that the question it raises is one you cannot put down once you have genuinely picked it up. The Fermi paradox is that question. It is the largest question our species has formulated, because it is the question of whether the universe is, at its deepest level, hospitable to minds. Whether the development of consciousness and technology and the capacity for cosmic-scale inquiry is something the universe embraces or something it reliably erases. And the silence, accumulated over 60 years of the most careful listening our civilization can manage, does not answer that question. It only makes it impossible to ignore. Stand on a hilltop at the edge of night, somewhere far from the ambient glow of cities, in a place where the sky still does what skies are supposed to do. Let your eyes adjust. The first stars appear individually, then in clusters, then in the slow revelation of the Milky Way's band. That faint smear of unresolved light that is the combined glow of hundreds of billions of stars, seen edge on, our own galaxy viewed from within. Spend enough time in that dark, and the sky stops being a ceiling and starts being a depth. You feel, in a way that is physical rather than merely conceptual, the scale of the thing you are embedded in. Now hold a single thought inside that feeling. Somewhere in that band of light, somewhere among those hundreds of billions of stars, each with its planets, each with its specific history of chemistry and collision and slow gravitational sculpting, somewhere in all of that, if the silence is what we think it is, there may be nothing looking back. Not the absence of life entirely, perhaps. Not the absence of microbial chemistry or simple replication, but the absence of minds, the absence of anything else that has arrived at the position we occupy, standing under a sky of ancient light, aware of its scale, capable of wondering what it contains, capable of building instruments to listen for an answer and finding, in the listening, only the long unbroken signal of the stars themselves. Hydrogen burning, helium forming, the same physics everywhere, the same chemistry, and from that chemistry, across 13 billion years of opportunity, perhaps only this: one small world, one fragile civilization, one species that learned to ask the question and has not yet learned whether asking was brave or futile. Stay with that for a moment. Do not rush to qualify it or soften it. Let it be as large as it is. The questions that remain, the questions that the evidence, examined carefully and honestly, leaves genuinely open, are not the comfortable kind of open questions, the kind that feel like invitations to optimism. They are the kind that open onto genuine uncertainty, and genuine uncertainty, held without flinching, has a specific weight that is different from fear and different from despair. It is the weight of things that matter and cannot be resolved by wanting them to resolve a certain way. What does it mean that we cannot know whether we are alone? What does it mean that we cannot know whether the filter is behind us or ahead? What does it mean that the science we have built, the extraordinary, cumulative, centuries-long project of understanding the universe, arrives at its most important question and returns an answer that is not an answer but a silence? Consider this. In the history of our civilization, silence has almost always been a context that other things fill. The silence after a question in conversation is filled by a response. The silence after a storm is filled by the return of ordinary sounds. The silence of a room you enter becomes, quickly, the sound of the building and the world beyond it. We are not adapted, culturally or psychologically, to silences that remain empty, that do not resolve into anything, that carry no hidden message waiting to be decoded. The silence of the universe is a silence of this unprecedented kind. It has been maintained across 6 decades of increasingly sensitive listening, across the full electromagnetic spectrum, across millions of candidate targets, and it has not been resolved. It has not begun to resolve. Every new instrument we deploy, every new analysis we perform, every new search method we apply, returns the same fundamental result. The universe, at the level of complexity that generates deliberate signals, or detectable megastructures, or biosignatures that hold up to scrutiny, the universe at the level of minds, appears to be extraordinarily, perhaps uniquely, quiet. And this is where something unexpected happens in the architecture of understanding. The silence, held long enough and closely enough, begins to change what you see when you look at ordinary things. The carbon in your body was forged in the cores of stars that died before the sun was born. The oxygen you breathe was released into a previously anoxic atmosphere by bacteria that lived 2.5 billion years ago and have been dead for most of that time. The neurons firing right now as you process these words are the product of a chain of evolutionary contingency so long and so improbable that its occurrence on this planet is, in the most literal sense, one of the most extraordinary things we know of in the universe. You are not merely in the universe. You are, by the best accounting we can do, one of the universe's most improbable achievements, an arrangement of atoms that has become capable of asking what it is and where it came from, and whether it is alone. This does not mean you are the most important thing in the universe. The universe, as far as we can tell, does not organize itself around importance. But it does mean that what you are, conscious, curious, capable of sustained inquiry into the nature of things, is either extraordinarily rare or extraordinarily precious, or both. And the silence suggests, with the kind of quiet insistence that does not shout and does not argue but simply remains, that the former is likely and the latter follows from it. There is a specific philosophical tradition that the Fermi paradox intersects at this point, and it is worth naming. It is the tradition that asks what our existence implies about the structure of the universe we exist in. The tradition of what philosophers call the anthropic principle in its various formulations. The weak version of the anthropic principle is uncontroversial. We observe the universe to have properties compatible with our existence, because if it did not, we would not exist to observe it. The stronger versions are more contested, but all of them circle around the same recognition. that the fact of our existence is itself a constraint on what the universe can be, and that the relationship between the observer and the observed is not as simple as it seems when you imagine the universe as a stage and consciousness as merely one of the actors on it. The Fermi paradox presses on this recognition from a specific direction. If intelligence is genuinely rare, if we are among the first or among the few, then our existence has a specific significance that the assumption of a universe full of minds would dissolve. A universe with one civilization is a universe in which that civilization's choices are freighted with a weight that does not apply when the choices of any single civilization are averaged out across millions of others. What we do in this universe might be among the very few things that minds are doing anywhere. The weight of that possibility is not comfortable, but it is not nothing. The astronomer and cosmologist Martin Rees, writing across multiple books and essays spanning the late 20th and early 21st centuries, has argued that the 21st century is, in a very specific sense, the most consequential century in the history of our species, not because of progress alone, but because it is the century in which the decisions made will determine whether humanity has a long-term future at all. Rees does not frame this as pessimism. He frames it as a calibration of attention, the recognition that certain choices compound forward in ways that are essentially irreversible, and that the window for making those choices well is not indefinitely available. This framing, the specific, time-limited character of the choices available to civilizations at the threshold we occupy, maps directly onto the structure of the Great Filter as a future barrier. If most civilizations fail in this window, they fail not because the universe is hostile, but because the window is genuinely difficult, and the choices genuinely consequential, and the margin for error genuinely narrow. And the specific difficulty of the window is not a feature of the universe's indifference. It is a feature of what intelligence is and what it produces. Capability that accelerates faster than wisdom. Power that outruns the institutions designed to govern it. Competitive dynamics that reward speed over caution in the short term, even when caution is what the long term requires. This is where the Fermi paradox becomes, not metaphorically but structurally, a mirror. Every observation about why civilizations might fail, the nuclear problem, the biotech problem, the AI problem, the coordination problem, is an observation derived from looking at our own civilization and asking what could go wrong. We are not reasoning about distant, abstract entities. We are reasoning about ourselves and using the silence of the universe as a frame for what that reasoning implies about our prospects. The silence does not tell us we will fail. Nothing tells us that. The Great Filter might be behind us. We might be rare and we might be safe. The cosmic youth argument might be right, and we might simply be early. The future might be genuinely open in the way that the most hopeful readings of our situation suggest. But the silence also does not let us assume we will succeed. It offers no precedent for success. There is no evidence anywhere in the observable universe of a civilization that navigated the technological adolescence we are currently in and came out the other side in a form that persisted and expanded and made itself visible. The absence of that evidence is not proof of failure. Absence of evidence is not evidence of absence, but it is the removal of reassurance. And a civilization making the choices we are making without the reassurance that others have made them successfully is a civilization reasoning from first principles in a domain where the stakes are total. Now we arrive at the question that the entire weight of this exploration has been building toward. The question that the silence, taken seriously, forces into view and will not allow to be avoided. What should we do with this? Not what we should feel. The feelings, the awe, the gravity, the specific quality of vertigo that comes from holding the paradox at full extension, follow from the understanding and do not need to be manufactured. What should we actually do as a civilization that has asked this question and arrived at an answer that is not an answer, but a wait? The first thing, and perhaps the most important thing, is to take the question seriously in proportion to what it actually implies. The Fermat paradox is not a curiosity for specialists. It is not a puzzle for astronomers to eventually solve while the rest of civilization goes about its business. It is a constraint on how we should understand our own situation. A reminder that the choices we are making right now, in the decade and century that define our technological threshold, may matter more than any previous choices in the history of our species. Not because they are dramatic, but because they are consequential in the specific way that the silence implies. They are the choices that determine whether we persist long enough to become visible to the universe we are trying to understand. The second thing is to maintain the search. The James Webb Space Telescope's capacity to detect atmospheric biosignatures in exoplanet atmospheres is genuinely new, genuinely unprecedented, and represents a qualitative shift in our ability to gather data relevant to the Fermi paradox. The Breakthrough Listen program's expanding network of telescopes and its increasingly sophisticated search methods are pushing the boundaries of what the null result means, making the null result more informative with every new survey. The Future Habitable Worlds Observatory, proposed as the next major space telescope after JWST, is designed with biosignature detection as a central scientific objective. These are instruments that could, in principle, shift the ground of the entire discussion. A confirmed detection of atmospheric biosignatures on a habitable zone planet, even one that stops short of claiming biological origin, would change the probability estimates in ways that make the Great Filter's location more constrained. And a confirmed detection of technological signals, a genuine, unambiguous techno-signature, would be, as has been argued, not a comfort, but a reckoning. The reckoning would be this: if they are there and they survived, then the filter may not be ahead of us, and the silence may be explained by rarity rather than destruction, and our future may be more open than the darkest readings of the paradox suggest. Or, if they are there and the signal is old and there is no continuation, if we receive a signal from a civilization that no longer exists, then the reckoning takes a different form entirely. The third thing, and this is the dimension that the Fermi paradox rarely reaches in popular treatments, but that the logic demands, is to treat the management of existential risk as a problem of the same order of magnitude as the question of cosmic life. These are not separate questions. They are the same question, viewed from different angles. The Fermi paradox asks why the universe is quiet. Existential risk research asks how civilizations fail. The answer to one is the other, and a civilization that takes the Fermi paradox seriously, that genuinely internalizes what the silence implies about the typical fate of technological civilizations, should feel from that internalization a specific urgency about the choices that determine which side of the filter it ends up on. This is not a call to fear. Fear is not a productive orientation toward risks of this kind. Fear produces paralysis and short-termism, and the kind of defensive behavior that, applied at the civilizational level, tends to make coordination harder rather than easier. The productive orientation is something more like deliberate attention, the application of serious cognitive and institutional resources to the problem of navigating the window of technological adolescence successfully, with the recognition that the window is real, that its successful navigation is not guaranteed, and that the stakes are not merely the comfort or prosperity of the current generation, but the existence of all future generations that depend on our navigation of this moment. The Stoic philosopher Marcus Aurelius wrote in the 2nd century that the obstacle is the way, that the things that block the path are not external to the path, but constitutive of it, and that the appropriate response to difficulty is not circumvention, but engagement. He was writing about personal virtue in a world of political complexity. But the structure of the insight applies at every scale. The difficulty of the window, the genuine hardness of the coordination problems, the genuine speed of the capability curves, the genuine insufficiency of existing governance frameworks, is not a reason to look away from the window. It is the reason the window matters. The universe, as far as we can tell, is not going to make this easier. It is not going to send a signal that tells us we are on the right track, or that the filter is behind us, or that others have navigated this successfully, and we can follow their path. The silence is not going to break into guidance. It is going to remain what it has always been: a profound, patient, unbroken absence of reassurance in a universe that does not organize itself around our need for comfort. What we have in place of that reassurance is the capacity to reason, to ask the question, to trace the logic to its conclusion, to hold the weight of the implication without collapsing under it or flinching away from it, to take the silence seriously, and from that seriousness, to draw the kind of attention and urgency that the situation requires. This is what the Fermi paradox ultimately demands of us. Not an answer, because the answer is not available. Not comfort, because comfort is not what the evidence provides. But a genuine, sustained, eyes-open engagement with the question of what it means to be here, in this universe, at this moment, in possession of this extraordinary and improbable and perhaps vanishingly rare thing called a civilization, and what our obligations are to the future that depends on our choices now. That is the full weight of the question that Enrico Fermi asked over lunch in Los Alamos in 1950. He did not know he was asking it at that scale. None of his colleagues did. The question has been growing ever since, as the search has expanded, and the null result has deepened, and the implications have been traced further and further into the territory of what they actually mean. The silence is not empty. It never was. It is full of something that has not yet been named with the precision it deserves. Something between warning and invitation, between elegy and challenge, between the record of what may have been lost and the description of what might still be preserved. The answer, if there is one, will not come from the sky. It will come, if it comes, from what we decide to do with the fact that the sky is, as yet, quiet. The silence began before we were listening. It will continue after these words have dissolved into sleep. And somewhere in the interval between the first stars and the last, in the vanishingly brief window that a civilization occupies before it either persists or does not, a species on a small rocky planet in the outer arm of an unremarkable spiral galaxy learned to ask the largest question it could formulate, and discovered that the universe, in all its extraordinary age and scale and chemical richness, was not yet ready to answer. Or perhaps it answered long ago, and the answer was the silence itself. Take a moment to look back at the full path of what we have explored together. Not to summarize in the thin sense of reducing complexity to a list of points, but to feel the shape of the whole, the way the different pieces fit together into something that is more than a catalogue of ideas, something that is a genuine, portrait of where we stand in the cosmos as best we can determine it. We began with the observation, the raw, empirical, 60-year-old fact that the sky is quiet. Not merely that we have not received a signal, but that the instruments we have built, the most sensitive listening apparatus in the history of our species, deployed across the full electromagnetic spectrum, pointed at millions of candidate targets, have returned nothing that holds. Breakthrough. Listen's analysis of thousands of stars. JWST's careful examination of exoplanet atmospheres. The Green Bank Telescope's survey of the galactic plane. The Parkes Telescope in New South Wales listening to interstellar visitors from beyond our solar system. The silence has been probed from every direction available to us, and the silence has held. We then built the framework that makes that silence strange. The Drake equation's honest accounting of our ignorance. Frank Drake himself, in 1961, standing at a chalkboard in Green Bank, West Virginia, writing out the structure of a question that has not been answered in the 65 years since. The numbers that should, given the age and size of the universe, fill the sky with signals, and do not. Adam Frank and Woodruff Sullivan's 2016 calculation suggests that 10 billion trillion civilizations may have arisen across the observable universe's history, making the silence not merely puzzling, but genuinely demanding of explanation. We traced the biological transitions that are candidates for the great filter in our past, the origin of life from chemistry, an event that took roughly 800 million years on Earth, and whose mechanism we still cannot reproduce in the laboratory. The eukaryotic transition, a single symbiotic accident approximately 1.8 billion years ago that produced every complex cell in every complex organism that has ever lived on this planet. The emergence of animal nervous systems across the Cambrian explosion, and the long subsequent path through vertebrates and mammals and primates to a species capable of building radio telescopes. Each transition is a candidate for the bottleneck through which most planets' evolutionary experiments do not pass. We examined Robin Hansen's Great Filter, the concept he developed beginning in 1996 that converted the silence from a puzzle into a constraint. The recognition that something in the long chain from dead chemistry to visible civilization is improbable enough that almost nothing makes it through. And the recognition, articulated with careful precision by Nick Bostrom, that every discovery of independently evolved complex life beyond Earth would be, in the most considered and rigorous sense, bad news, because it would move the filter from behind us to ahead of us, from the domain of our evolutionary past to the domain of our civilizational future. We catalogued the hypotheses. The rare Earth view, where the conditions for intelligence are so specific that they converge almost nowhere. The dark forest, where civilizations exist, but hide and destroy to survive. The zoo hypothesis, where we are observed and protected by minds that have chosen not to announce themselves. The transcension hypothesis, where advanced minds turn inward rather than outward. The Gaian bottleneck, where most planets that develop early life lose their habitability before complex life can arise. The Berserker hypothesis, where self-replicating probes clear the galaxy of emerging civilizations on behalf of an original creator that may long since have ceased to exist. The cosmic youth argument, where we are simply early, and the universe has barely begun its experiment in complexity. None of these resolved the paradox cleanly. Each carried its own internal logic and its own weaknesses. Each illuminated a different facet of the same central question. And the pattern that emerged from the catalogue was one that no comfortable account of the Fermi paradox can accommodate. The explanations that most satisfyingly fit the data tend, with a consistency that is itself a kind of signal to be the ones with the most sobering implications for us specifically. We examined the specific mechanisms by which technological civilizations might fail. The nuclear window, the biotechnology window, the artificial intelligence window, and the degree to which our own civilization is currently situated within all three simultaneously. The near misses that populate the nuclear era: Vasily Arkhipov in a Soviet submarine in 1962, Stanislav Petrov at a monitoring station in 1983, each holding a decision that civilization's continuation depended on, each choosing, for their own reasons, in their own moments of irreducible individual judgment, to hesitate when protocol called for action. The gaps in the biological weapons governance architecture. The acceleration of AI capability against the backdrop of governance frameworks that have consistently lagged behind the pace of development. And we arrived at the mirror. The recognition that the Fermi paradox is not merely a question about the distribution of civilizations in the universe, but a question about what kind of things civilizations are, whether they reliably develop the wisdom to manage the capabilities they generate, or whether the mismatch between capability and wisdom is a near universal feature of technological development that functions as a filter in itself. A filter that does not look like a disaster from the inside. A filter that looks like progress. What remains at the end of all this is not a resolved question, but a clarified one. The question is no longer merely, where is everybody? The question is, what does their absence tell us about the nature of what we are, and the nature of what we face, and the nature of the universe we find ourselves navigating without a map and without precedent? The stars are old. Some of the light reaching your eyes tonight left its source before Earth existed. Some of it left before the solar system had begun to condense from its parent nebula. The universe has had 13 billion years to run its experiment in complexity, and on the evidence available to us, it has produced in all that time one instance of a civilization capable of examining the results of the experiment. That instance is us. That examination is this. There is something in that fact that resists easy categorization. It is not purely consoling. The weight of what the silence implies is too real to be dissolved by the observation that we are extraordinary. But it is not purely grim either. The existence of consciousness in a universe that might have contained none. The emergence of curiosity in a cosmos that did not require it. The specific and improbable beauty of a mind that can hold the question of its own rarity and feel the full force of what that rarity means. These are not small things. They are, on any reasonable accounting, among the most remarkable features of the world we inhabit. Martin Rees, in his reflections on the fragility and the potential of our civilization, has suggested that the decisions made in this century will echo across cosmic timescales. That what we do now, in the narrow window of our technological adolescence, will determine whether the universe continues to contain at least one example of the thing we are. That framing carries a weight that is easy to deflect and difficult to carry, but it is not a hyperbole. It is a derivation from the structure of what we know. The ancient Greek astronomers who first mapped the stars and gave them names, Hipparchus, working at the island of Rhodes in the 2nd century BCE, cataloguing more than 800 stars with a precision that would not be surpassed for centuries, did not know what those stars were. They knew them as lights, as navigational references, as the backdrop for mythology and calendar. They had no concept of stellar nuclear fusion, no concept of planetary systems, no concept of the possibility that other suns might host other worlds. The question they could not ask was precisely the question we are asking. And the distance between their horizon and ours, the distance that the accumulation of human knowledge has crossed in 2,500 years, is a measure of what intelligence can do when it persists. This is the thing the silence cannot take away. It cannot take away the fact of this, the existence of understanding, of inquiry, of the capacity to stand under a night sky and feel the full weight of what it contains and what it implies. It cannot take away the chain that runs from the first self-replicating molecules in ancient oceans to the civilizations that now sit in the dark and wonder whether they are alone. Whatever the filter is, wherever it lies, we have arrived at a point that the mathematics of the universe did not require, and the laws of physics did not guarantee. We are here. We are asking. And the asking, in the vast silence of a cosmos that does not ask its own questions, is not a small thing. The silence is not an answer, but it is not nothing. It is the largest context in which we have ever placed ourselves, and the placing changes the view. The mundane world, the decisions being made in government chambers and corporate boardrooms and research laboratories, the choices about how to govern the technologies being developed, the choices about how to coordinate across the collective action problems that define our current civilizational challenge. These decisions look different when they are held inside the frame of the Fermi paradox. They look like what they are, the specific, time-limited, consequence-laden choices of a civilization navigating the window that the silence implies is difficult, and that the absence of any cosmic precedent confirms has no guaranteed outcome. The filter is real, in at least the minimal sense that something must account for the silence, whether it lies behind us or ahead, whether it is biological or technological or physical or structural, whether it is something we have already survived or something we are in the process of encountering. These questions remain open. They may remain open for a very long time. They may, in some of their dimensions, remain open forever, because the universe does not offer its deepest truths in the form of clean experimental results. What the Fermi paradox offers instead is a question of a specific and irreplaceable kind, the kind that changes the questioner in the asking of it, the kind that cannot be unasked once genuinely posed, the kind that makes the familiar world strange and the strange world urgent, the kind that places your existence, this specific existence, in this specific moment, on this specific small world, inside the largest frame that human thought has yet constructed, and asks what you will do with the weight of being here. The stars will continue their ancient burning regardless of the answer. The galaxy will wheel through its rotations on timescales that make civilizations brief. The universe will continue its expansion, carrying its galaxies apart from one another at speeds that will eventually, across billions of years, make them unreachable from any other. The cosmic context is indifferent to outcomes in the way that physics is indifferent, not hostile, not supportive, simply governed by laws that do not bend in response to what we need them to say. But indifference is not the final word. The final word belongs, if it belongs to anything, to what consciousness does inside the indifferent cosmos, the specific, improbable, perhaps extraordinarily rare capacity to look outward and inward simultaneously, to ask the question that the universe does not ask of itself, to hold the weight of our own contingency without being crushed by it, and to decide, in the full knowledge of what the silence implies, to keep listening. The Milky Way is turning overhead right now, as it has been turning for 5 billion years, as it will continue turning for billions more. The 200 billion stars within it are carrying on their patient nuclear burning, each one a sun, each one perhaps with worlds, each one perhaps with the chemistry of possibility. And across all of that, across the full span of what we can see, and what we can infer, and what we cannot yet imagine, the silence holds. It It is the loudest thing we have ever heard. If this changed how you think about the universe we inhabit, about the silence, about the weight of being here, about the choices that might matter more than any others in the history of our civilization, then the time we spent together was well spent. Thank you for staying, for remaining awake or half awake inside this question, for carrying it with you into whatever comes next. The stars are still there. The silence is still there. And so, remarkably, are you.